Hello wonderful person, this is Anton, and in this video we're going to be talking about various signs that allow us to understand or see if there is alien life on certain planets out there. But more specifically, we'll talk about this one molecule that the scientists now believe is a telltale sign of alien life. So obviously, if you're an alien species trying to analyze the atmosphere of Earth, you would discover that there's some really strange patterns of oxygen and carbon dioxide and a lot of other gases such as methane that seem to suggest that there is something life-like going on the planet. The biggest sign here is of course oxygen. So in some sense, the detection of oxygen on various planets can indicate that there's maybe life. But oxygen is also produced naturally. More specifically, the solar radiation, for example, can easily create oxygen by striking the molecules of water. There's other ways oxygen can be produced, so just detecting oxygen on a planet somewhere is not a sign that we've just discovered life. And something similar is true of molecules like methane, which for example Titan has a lot of. But even though we've detected methane on Mars, we've detected methane on Titan, and some of it is a little bit unusual and hard to explain, it could technically be also produced naturally, without using any life or any kind of bacteria. So in that sense, neither methane nor oxygen nor any other organic molecules that are commonly associated with life here on Earth can easily be said to be produced by life, because we've detected many of these molecules out there in space, often around various asteroids, comets, or even just in the middle of various gas clouds. And for the past few years, scientists have been actively trying to identify these so-called fingerprints of life, essentially various molecules that can be identified as biosignatures, as only produced by life. They've already looked at something like 16,000 various molecules, and they've identified at least one such molecule that seems to be exclusively produced by life, at least on terrestrial planets. This molecule right here, known as phosphine, has been recently identified in the study as the telltale sign of a biosignature most likely only produced by life, more specifically non-oxygen related life that would be almost impossible to explain in any other way. So first of all, this molecule is found in many different locations on our planet, but it's found in very strange and very unusual places and produced by life, such as for example in various types of fish inside their bellies. It's also found produced by bacteria inside penguins and normally can be found inside their dung, or basically their poop. And for the most part is directly associated with bacteria that doesn't really like oxygen. In other words, the so-called anaerobic bacteria that was a lot more prevalent on our planet early on, when the oxygen was still not really in existence on the surface, but there was a lot of other materials including methane. But even today, the presence of phosphine is always associated with some sort of life, either life inside the fish guts, or the life inside penguins, or some other bacterial life that eventually ends up producing a lot of phosphine as a kind of a leftover. Because for the most part, any aerobic or oxygen breathing life on Earth doesn't really want anything to do with this molecule. Phosphine is known as a stinky gas, it's also super toxic, and it's also a flammable gas. But what's I guess most interesting is that it's always produced by various anaerobic or non-oxygen bacteria that's present here on the planet and is never produced in any other inorganic way. And the MIT researchers, specifically Clara Sousa Silva, who was the main researcher behind the study, essentially tried to create this in any way possible. They actually analyzed this gas in many different ways, and she even studied this very thoroughly for about 10 years. And in all of her discoveries, she discovered that there were only two major ways this gas is produced in the galaxy. Either inside really massive gas giants through some really extreme means and under a lot of pressure and temperature. So basically both Saturn and Jupiter have quite a lot of phosphine in the atmosphere that can be detected with various probes. Or it's produced here on Earth, but only by life. Nothing else seems to be able to produce this molecule in any other way. In other words, let's just say that we find phosphine in the atmosphere of Mars. This would be a telltale sign that there is bacteria that's producing it and not any other geological event, suggesting once and for all that Mars definitely has life. Now, we obviously haven't found it yet, but the scientists behind this paper also identified very specific light signatures that phosphine would produce that could then be detected by various telescopes in the future. On top of this, the scientists have also established a very thorough analysis of molecules that can be used in the future to identify other bias signatures as well, allowing us to expand the list of bias signatures in the near future and very likely establishing the list of molecules that could be telltale signs of life on other planets. Now, if we were to actually try to analyze the chemistry of phosphine and try to figure out why is it that only life produces it and why can it only be produced in the middle of really extreme places like inside gas giants, and in simple terms, it really has something to do with the hydrogen molecules that you see right here not liking to stick to phosphorus in the way that it's created here. In other words, you need a lot of energy and a lot of extreme conditions to generate this molecule. It doesn't really like forming like this naturally, unless of course it's also created inside bacteria that find various pathways to then generate this molecule in different ways. So in a nutshell, it can either be created by bacteria or in really extreme conditions. Naturally, it just doesn't appear otherwise. And because it requires so much energy to produce, it also releases energy and burns really easily, which is why it's a flammable gas. And the good news is that because of this study, the scientists were able to create very thorough analysis techniques for the James Webb Telescope, and so when it launches in 2021, we'll actually be able to use this technique to detect any kind of signatures of phosphine within about 16 light years away from Earth. And with the sun right there in the middle, you can see some of these stars right here on the screen. So within about 16 light years, we'll be able to identify any kind of phosphine-related life signatures by using the telescope's new devices and by also using the technique from this study. So if suddenly we look at the nearest exoplanet to us, Proxima b, and discover that there is phosphine light signatures coming from it, there is no other explanation at the moment. The only explanation is that there is bacterial life producing phosphine, and this gives us more reason to launch a probe here to try to investigate this discovery. And so that's really one of the major discoveries coming from the study, and this is something to look forward to when James Webb Telescope launches in the future. Hello wonderful person, this is Anton, and in this video we're going to be talking about the new types of objects known as G-objects. These very unusual and very peculiar star-like objects that orbit very close to the central black hole and don't seem to exist anywhere else. This beautiful picture created by Jack Quirlo of UCLA kind of shows us what these objects might look like, at least what we think they look like. But what exactly are they? Well, if you look at the center of our galaxy, you'll discover a really extreme environment. There's a lot of things happening here, a lot of them are extremely energetic, and a lot of life would probably not survive here for a very long time. Even though simulations like this present this region as somewhat similar to what we see around us in where our sun is, in reality the energies here are so dramatic and everything is so extremely chaotic that most planets and most stars very likely get destroyed really quickly. And the closer to the central black hole you get, the more dramatic things get. So a few years ago, the scientists observed a passage of what's known as G2 cloud very close to the black hole that resulted in the formation of unusual gas that very likely fell into the black hole. But we didn't really know until now what exactly is happening here. And more specifically, we had no idea where this cloud came from and if there are other similar clouds around the black hole. We actually knew about at least one other cloud known as G1, but it didn't really have such a dramatic shift as we've observed with the G2 cloud that came very close to the black hole, probably the closest so far. And so it took a few years for the scientists to try to figure out what exactly this is and how this may have been created, and more importantly, if there are other similar objects in this region. And as you can probably tell from the title, there are. There are at least 6 now. These scientists from UCLA discovered at least 4 more of these G clouds and were actually able to identify their peculiar features and explain how they may have formed and why they exist in this region. And the major feature of all of these objects is that they tend to stretch out and become a lot more longer, losing a lot of mass as they get closer to the black hole, while as they move away they become compact again and resemble star-like objects. And this is what makes them so unique and so unusual and very different from anything else in this region. And to try to understand all of this, we have to also understand that there are a lot more stars and a lot more material in this region. As a matter of fact, the average density in this region is about 1 billion times larger than it is where we're located. In other words, this is a tremendously hectic environment. And because of this, there's a lot of different stars, and some of these stars might come as binaries. In other words, stars that come as a pair and orbit around one another, which actually represents a lot of different stars out there. The nearby Alpha Centauri is actually a binary star. There are 2 objects in the system. But one thing we know about binaries is that if you place them around a much larger and much more gravitationally potent object, they will eventually start acting a little bit strange. So here's an example. Let's take a star and place it in orbit around the black hole. Notice how its orbit is relatively circular, even though in reality it would still be kind of hectic. But now, what if I turn this star into a binary system? Basically, I place another object in orbit around the star. Well, because of the dramatic tidal effects and a lot of gravitational power that this black hole possesses, these stars will no longer be attached to each other, and eventually they'll probably either fly apart or might end up combining into one. And this combination of 2 stars will actually result in the formation of a somewhat exotic object. Now here, I think if I actually leave them running, they'll probably just create a supernova, but that's not what we're looking for. We're looking for a kind of an intermediary object, basically a massive amount of gas that's not necessarily a star because it never really gets to form into a spherical object, and is not a cloud either. So it's kind of like an in-between state. It's a cloud and a star at the same time. When it's closer to the black hole, when it's approaching its so-called periastron, or the closest part of the orbit, it will eventually get stretched and turn into a very long, dusty object. But then, as it moves away from the black hole, it very likely will start condensing again and form into more of a star-like object. But because its orbit probably takes anywhere from a few decades to maybe a few hundred years or maybe a few thousand years, it never truly gets to solidify into a single piece or an object that can survive for much longer when it comes so close to the black hole. And this, in the essence, is what these G objects are. The scientists behind this paper believe that they originally were binary objects, binary stars. And eventually, through the interaction with the black hole, they kind of stretched, they started to become a lot more unstable and became these very unusual, permanent, stretchy objects. Basically, not really clouds, not really stars, but a bit of both. So they do possess cloud-like shapes and possibly have a lot of cloud-like features, but in the middle they do have these solid objects that kind of possess a lot of mass that eventually pull all of the material back in, creating a star-like object when it's farther away from the black hole. And even though these objects kind of look like a gas cloud, they for the most part behave like stars, and actually remain star-like for most of their orbit. Their orbits can be anywhere from 100 to a few thousand years, and most of this time they do behave like typical stars. Now you might have seen a video I made previously a few months ago about the flares in the middle of our galaxy coming from the supermassive black hole in the center, and these flares are still unknown. Back in August, our black hole essentially became extremely bright for a little bit and then started to dim once again, and the scientists believe that there is a possibility that G objects are responsible for these effects. Basically, as some of the material falls into the black hole, it will create these unusual flaring effects. So it's possible that what we're observing is the eventual interaction between Sagittarius A star, the supermassive black hole in the middle, and the G objects that pass there every few hundreds or thousands of years. And even though a G2 object came really close to the black hole, a lot of other G objects never really come that close, but nevertheless possess very similar features. They get stretched out a little bit and then become a lot more compact when they're farther away from the black hole. So all 6 objects discovered so far seem to possess very similar properties, making them an actual object that's different from typical stars, binary stars, or any other objects we normally are familiar with. From what the scientists observed so far, they seem to be going from in between these really stretched and distorted objects when they come really close to the black hole to looking like normal typical stars when they're much farther away. And this is what makes them so unique. They are very dynamic and they do change in time. And because things are really far away here, this is about 26,000 light years away from our solar system, it's going to be really difficult to try to identify how they formed, what other effects they have on other stars and the black hole itself, and most importantly, if they can create effects that would be so dramatic that it could somehow affect our solar system and our planet. Now, that's probably unlikely, but we still need to study them in a little bit more detail. And when it comes to star mergers, today we believe that a typical star merger should take about 1 million years to complete. So if a binary star approaches the black hole and its orbit is only a few thousand years, it's never truly going to combine into a single star and will always remain as a kind of a binary mixture, and this is what we believe is happening here. And since our galaxy in general has so many different binary stars, and at the same time since it's quite possible for many binary stars to combine into one star, this could be an explanation to many different other mysteries we're observing around the galaxy that we still can't really explain. So for example, certain stars out there, like the so-called oldest star in the universe, might have been a result of a very unusual binary combination. Basically, when two stars join together and mix their material, they'll eventually turn into something completely different, something that we wouldn't be able to explain right away unless we knew that this is exactly what happened. In other words, by using binary stars and by using the basically joining of two binary stars into one, we could maybe explain a lot of other mysteries that we're not really clear about just yet. But more importantly, in regards to this study, we now understand that this particular simulation created by ASO a few years ago might not really be that accurate. It seems that the gas itself did not stretch as much as is presented in this video. As a matter of fact, it seems that only the outside part of the gas was stretched, but the inner part of the object remained as a solid part, as a kind of a star-like object. In other words, once again, resembling something similar to what you see in this beautiful illustration. Some of the projections here are formed by the outer gas and some of this will end up in the black hole, but the vast majority of mass here, including the inner part, will still remain as a kind of a star-like object, very likely still producing energy and a lot of light, similar to a typical star. And of course, what's kept it all together is this inner mass, this stellar object on the inside, which all of the G objects seem to possess. And so the next question now becomes, are we going to be able to find these objects elsewhere in the galaxy or in the universe? Or is this uniquely only the object you can find close to supermassive black holes? Would we ever be able to find a very similar object somewhere else? Hello wonderful person, this is Anton, and in this video we might be able to finally answer one of the mysteries of the universe, at least in regards to the formation of very large massive stars. In other words, we might be able to explain how all of this happens based on a new observation. Now, some of you may already know the answer to this, but do you know what the most massive star that we've discovered so far is? And also, where exactly is it located? Well, it just so happens that obviously there's a video about this sometime in the past where I made it a few years ago, but let's actually go there right now. If you were to look around the night skies, you would discover the neighboring galaxy known as Large Magellanic Cloud. It's actually somewhere right there. And inside of this galaxy, there is a region that's essentially a kind of a molecular cloud. It's generating a tremendous amount of very large, very massive stars, and it's also going to be one day responsible for generating some of the more beautiful and more energetic supernova. In this region, somewhere right there, is a star known as R136A1. To date, this is the most massive and pretty much the most energetic, bright, and so on star we've discovered. It's possibly over 300 masses of the Sun, and it's so bright and so powerful that we are not even entirely sure how massive it is. And I actually decided to dim it a little bit because it's just a little bit too bright. And the thing is, there are a lot of similar stars in its neighborhood. R136 is a system of very massive stars that were created in a roughly similar period of time and in a similar region as well, not so far away from one another. But the thing is, we don't really understand, or at least didn't understand, how exactly some of these more massive stars form. So in other words, why is it that some stars end up being so huge and so massive while others are more similar to main sequence stars like our Sun? What mechanism causes these stars to acquire such a dramatic amount of mass in such a short time? And one of the main reasons we don't really understand how they form is because we generally think that all of the stars are formed in a very similar fashion. It all starts with a gas cloud that slowly condenses into a much thicker cloud, eventually forming some sort of a shape that then ends up being a protostar. These protostars we've discovered quite a lot of. Here are just some of the images released by the scientists in the last few years, and there are a lot more of these, and they all seem to actually be kind of similar. Which in a sense suggests to us that we do understand the formation of stars relatively well. But there is a small problem. If these protostars become what we believe they become, essentially they turn into this type of a protoplanetary disk with a star in the middle that's about to become nuclear and start producing a lot of energy, we think that as soon as it actually turns into a star, and here I'm going to try to simulate this using Universe Sandbox, so as soon as this object here becomes an actual star, it starts generating so much solar wind and so much energy that essentially all of the other dust and all of the material present around the star system will slowly start moving out of the system and eventually become completely ejected from it. That's our general understanding of how protoplanetary systems form and how they then go from this to a much more familiar star system such as, of course, the solar system. But then the question here is, if this mechanism works for all of the stars, how do some stars become so much more massive? What prevents them from losing the material and from basically becoming small like our sun? What's making them continuously grow more massive, reaching sizes of 300 masses of the sun? That's actually where the mystery is. The mystery is, how does all of this gas still stay here and then ends up inside the star? And so to answer these questions, the scientists obviously have to look at something we've never seen before, or at least we've seen very few times. There's a very rare type of an event that we often refer to as the accretion burst event. We've only observed very few of them, and we were lucky enough to see just another one very recently. And in a nutshell, to try to understand how this event works and how this makes the star grow, imagine once again the typical protoplanetary star system. In many of these disks, there is a lot of gas that still kind of circulates around the star system and is still attached gravitationally to the system itself. And once in a while, this gas reaches a kind of a critical mass where it starts suddenly flowing into the star. And interestingly, all of this mass is somehow funneled right into the middle where the star suddenly absorbs all of it almost instantly. In other words, even though we usually imagine these stars kind of growing gradually over time and acquiring mass relatively slowly, in reality it seems that most stars actually acquire their mass in very huge bursts of mass suddenly coming into the star, and in many cases this burst continues over and over until the star reaches really large masses. And even though we've only seen very few of these events, the actual observations are always relatively similar. We seem to observe quite a lot of so-called masers, so sort of like lasers, but instead of visual light, they're produced in microwave light. In other words, they're only visible to radio antenna or special telescopes that can only operate in microwave frequencies. But technically you can have a very similar concept to a laser in any frequency, and in this case it's the microwave. And so what the scientists behind this paper observed was a sudden burst of masers coming from this particular system. And all of the modern models suggest that masers usually indicate a very unusual burst event. And the current explanation kind of goes as follows. So because there are a lot of various layers around the star, various material is still kind of there, as the burst occurred initially, some of the material started to propagate through these various layers, and more masers started to be generated over the following weeks. And as more masers were detected, this only suggested how much power this event had. And the only explanation to such a sudden increase in energy is if suddenly the star absorbed a lot of matter and generated all of these masers. In other words, this was an accretion burst that suddenly increased the mass of the star quite dramatically. And the scientists behind this paper also believe that there's probably a lot of different burst events, all of which generate different types of energy and also all of which might produce different types of stars in terms of mass. In other words, some burst events will produce stars similar to our sun, but some burst events will produce something along the lines of R136A1. And all of this of course depends on how much gas there is around the star originally and on the frequency of these events, as well as the total mass that the star is able to absorb. We can try to see what we can generate here in Universe Sandbox by essentially trying to create our own burst event right here. And as you can see, this whole energy that was released will now, as it travels through the protoplanetary disk, start emitting various masers that can then be detected on our planet. And as this happens more and more often, the star will eventually grow larger and larger in size. Although I guess for a star like R136A1 to be generated, a huge amount of these events need to happen relatively in a short period of time, which of course means that a lot of gas needs to be present in the vicinity. Nevertheless, by discovering these burst events and by seeing how stars are created, we are now in a much better position to explain how exactly all of this is created and why some stars are so much more massive than our Sun. And although it's going to be a few years before we can finally confirm how all of this happens, for now we have to rely on the current observations and of course on all of the data we've collected over the years. And once new telescopes like James Webb Telescope become operational, we'll be able to actually see this in a lot more detail and possibly even detect actual collisions as they happen in more or less real time. But until then, and until we get better telescopes, we have to rely on the current understanding and current theories. But in that sense, we now might have a much better idea of how massive stars are generated. And this also, of course, confirms the general idea we have about the formation of stars, the idea that the stars do form in bursts, and some of these bursts are really energetic and extremely powerful. So powerful that we can see them from planet Earth, even if they're really far away. This star, by the way, is over 22,000 light years away, and we were able to see all of the masers that it sent toward us. Hello wonderful person, this is Anton, and in this video we're going to be talking about this recent study that was able to discover the so-called invisible star, a star that's not typically visible in the night skies. But to find this star, they used a very interesting technique. Now, when I look into the night skies, I don't really see that many stars, mostly because my vision is pretty bad, so for me a lot of stars are invisible. But obviously if you have a very powerful telescope, you're going to be able to see quite a lot. And the more powerful the telescope, the more stars you're going to see. So at some point, if you were to magnify our galaxy by a tremendous amount, you'll be able to see stars that were previously invisible to us. And a few years ago, actually more like a decade ago, the scientists used the so-called WISE survey to discover quite a lot of different stars that were practically out there all this time, but we just didn't see them. Specifically here I'm talking about the so-called brown dwarfs, the closest one of which is this right here. This is a binary system known as Lyman A and Lyman B. These are brown dwarfs that are just over 6 light years away from us, so basically they're really close to us. But they're very difficult to see unless you have a very specialized infrared telescope. And this is how the scientists were able to discover them. So now we know that there's quite a lot of these brown dwarfs in the vicinity, and we were able to discover quite a few of them even very close to our own solar system. But this is not what we're talking about today. Today we're talking about a different type of invisible star. It's a typical star very similar to the closest star to us, Proxima Centauri, a typical red dwarf. But the thing is, if this red dwarf was really far away from us, we would obviously not be able to see it at all. However, a few years ago, there was a very interesting event known as Gaia 16AYE. This event was essentially a sudden brightening of a star in the region that you see right here in the night skies. And this brightening didn't just happen once. As the scientists were observing this for several weeks, they witnessed this 5 different times, which actually is very unusual. And just to help you visualize what the scientists were seeing, they were looking at a star, a relatively bright star, known as 2MASS 9040. As they were looking at it, suddenly the star very briefly brightened, and then, just like that, went back to its original brightness. Then, a few weeks later, it did so again. And then, again. And then, again. And as this kept happening, the scientists realized that what they're probably observing is a very typical but very mysterious gravitational lensing effect. Mysterious because they weren't really sure what was causing it, but these effects or these phenomena are pretty familiar to us. Gravitational lensing is how we actually did discover quite a lot of different exoplanets, and we've also found a lot of other objects and even the most distant star to date. Now, gravitational lensing works on a very simple principle. When there are 2 massive objects and one of these objects passes in front of the other, the brightness of the object behind will actually increase because of what's known as Einstein's lens or a gravitational lens. The way that this works is basically as follows. This is a simulation that NASA made a few years ago, and here you can see that basically as this object passes in front of the other star or other visible object, it sort of bends the light, creating this very beautiful ring-like formation that we often refer to as Einstein's ring. Now, by looking at this particular star, the scientists were able to predict that this is exactly what's happening here, and they were pretty excited about it, but the scientists from Poland were not satisfied with this, and decided, a few years later, to release this paper with quite a lot of authors in it that essentially analyzes and discusses what exactly caused this gravitational lensing effect. And by the way, this is probably the most authors I've seen on the paper in a very long time. Now, in a nutshell, we're not really particularly concerned with the star that we're looking at. Basically, the 2-mass 1940 star is not really that important, but we are interested in the object that caused the gravitational lensing effect, because the study that I just mentioned was able to create a very interesting way for us to analyze these gravitational lenses and find out what exactly is causing the effect, and thus use these techniques to discover more objects that are technically invisible to us. So what exactly did they discover? Well, as you can probably imagine, it's not really a black hole, because I would have been a lot more excited about it. It's also not a neutron star or any other unusual object, such as, for example, brown dwarf or any other compact object like a white dwarf, but it is nevertheless a pretty interesting system. It's a binary red dwarf. More specifically, 2 red dwarfs that are orbiting around one another and are also approximately 57 and 36% the mass of our own sun. In other words, if you were to combine them together, it would be very close to the mass of our sun. But the scientists didn't just stop there. They were able to very accurately estimate not just the mass of both stars, but also how long they take to orbit one another. In other words, they were able to very precisely analyze the entire star system here with just those 5 observations of a gravitational lens. And they discovered a system of 2 stars, with stars taking about 2.8 years to orbit around one another, and all of this at a very far away distance of about 2500 light years away from our planet. And because these are red dwarfs, at this distance there's just no way we would see them otherwise, simply because they're just way too dim in comparison to anything else we're used to. And honestly, this technique is super exciting, mostly because it can actually allow us to discover a lot of other invisible and technically otherwise impossible to see for us objects. Obviously, we expect to find at least a few black holes this way. As of today, we haven't really seen any so-called invisible solitary black holes, even though we expect millions and possibly even billions of them in our own galaxy. Unfortunately, as of today, the only possible detection of what's known as a primordial black hole, or really any kind of a black hole out there, was actually last year with a Japanese team that detected a very unusual gravitational lens from the Andromeda galaxy. And this could have been potentially a black hole, but we're not entirely sure and there's no way for us to check just yet. But by using this technique, and more importantly perfecting this technique and even automating it, and also creating telescopes that are able to observe the night skies, or I guess around the clock 24/7, we could one day discover a lot more of these unusual objects, including black holes, including other planets and other stars that are otherwise invisible to us. And this is also one of the ways we could potentially discover the elusive Planet 9, by looking around the night skies and detecting the gravitational lens from a region where we don't expect it to happen would allow us to almost definitely discover an object that's otherwise invisible. In other words, this technique is possibly the future of astronomy and various astronomical observations, simply because it allows us to magnify the light by a tremendous amount. As I mentioned previously, the farthest star we've discovered, billions and billions of light years away from us, was actually discovered using gravitational lens technique, and completely by accident. So once we perfect this technique, and once we're able to predict when these gravitational lenses occur, we'll be able to dramatically increase the detection of various objects, various planets, various unusual hidden objects in the solar system, and most importantly, possibly even discover these elusive black holes that should be out there but we're just not seeing them. As a matter of fact, the only black holes we've seen so far, except for the supermassive ones, are the black holes in binary systems, where they actually get to absorb a little bit of the mass from their partner and thus emit a lot of radiation. But unless they're emitting radiation, they're pretty much invisible to us as well. And interestingly, because of this study, they were also able to predict the next time we might be able to see this gravitational lens again, which is why the scientists are going to do their best to try to observe what else is in the star system and thus perfect this technique even more. We expect this to be visible sometime in 2021, and by then we're hoping to have some sort of an automated system, maybe even connected to the very famous Gaia observatory, thus being able to detect everything in real time and with a lot of precision. So if all goes well, in the next few years we'll be detecting a lot more objects, and actually a lot of really interesting objects that we've never even seen before, or at least never been able to see before. So if all goes well, in the next 5 years we'll have a tremendous amount of new data and a lot of new studies coming out, allowing us to understand our galaxy and the universe a little bit better. Hello wonderful person, this is Anton, and in this video we're going to be talking about an incredible new discovery of a very strange exoplanet where it seems to be raining only in the evening, and the rain itself is actually made of iron. In other words, it's a very unusual, extremely hot planet. In the last few years we've discovered so many of these so-called hot Jupiters where things are just really weird. The majority of these hot Jupiters orbit extremely close to the parent star, so the actual atmosphere becomes very different from anything here in the solar system. For example, we discovered planets where there seems to be a kind of a unusual titanium atmosphere that seems to actually cool down the surface but heat up the atmosphere itself. We've also seen these so-called cotton candy planets that, despite relatively small mass, seem to have really large size and thus very low density. And in one of the previous videos I've even found out that apparently their density is even lower than cotton candy. So these are super thin and unusually cloudy objects. And so in reality they resemble somewhat unusual hot clouds than they do actual planets. And we've also discovered unusual egg-shaped planets where scientists even think that we shouldn't even be calling these planets anymore because half of these objects does not even have any atomic structure. They do act like plasma, not really like matter anymore. And so in that sense there are a lot of really unusual and strange objects out there, and usually the strangeness begins when the planet orbits really close to its parent star by being tidally locked and always having the same face toward the star, while the other face seems to be pointed always at the night skies. And because these planets are so massive and so easy to see compared to other planets, we've found quite a lot of them. Unfortunately, we don't have anything like this in our own solar system, but there's definitely tons of them everywhere else in the galaxy. And although we've predicted that some of these planets can even be completely pitch black on both sides, and some of the darkest planets in the universe maybe, not all of them seem to qualify as the darkest planets, and some of them do have unusual features. And what's more interesting is that some planets like WASP 76b have just the right temperature to be even stranger. And more specifically, the scientists uncovered that this planet here has very specific rain at very specific, I guess you can call it, time of the day. By using European Space Observatory's new telescope known as Espresso, the scientists were actually able to very accurately see what's happening in the atmosphere of this planet. And they discovered that it's raining, but only in the evening. And the rain itself is not water, but actual molten iron. And it's very clever on how they actually discovered all of this, and essentially how they found out that it's basically only in the evening as well. So in other words, if we were to look at the planet here, if we were to try to analyze its actual structure, because here it's spinning counterclockwise and because it's always facing with the same side toward its star, it's always going to have, I guess you can call it, morning on this right side here, and then it's always going to have evening on the other side, the left side. And obviously the opposite side here would be the nighttime. And so the morning side seems to not really have anything, while the night side or the evening side does have a lot of iron rain. And the best explanation that the scientists could propose for this is that, well, there is a lot of iron in the planet, but it always essentially gets molten right here on the brightest and the essentially hottest side of the planet, which is right in front of the star itself. So this is, I guess you would call it, the noon side of the planet. The temperatures here are roughly around 2400 degrees Celsius, which is about 4300 degrees Fahrenheit, and this is right between the temperature where iron melts and also where iron starts boiling as well. At some point, those iron clouds that develop on the bright side, due to the really high velocity of the winds, reach the side of the planet that you would consider evening, so basically the slightly cooler side. This is where the temperature drops and the clouds themselves start to precipitate, and basically you get molten iron rain. And so when you think about it, this is literally a liquid cycle, kind of like what we have here on Earth, kind of like what we've seen on objects like Titan, except that it's not water there, but usually methane. And this time we have something similar with iron. Now this would not really be possible if the temperature was any lower or even any higher, because with temperatures that are higher, this is where you start getting plasma and the planet starts to become really deformed. This is some of the previous planets we've talked about. You can check out some of the previous videos I made about these discoveries as well. But instead what we have here is a very interesting temperature gradient between the bright side and the dark side. There seems to be a temperature difference of a few thousand degrees. Specifically, the dark side is about 1500 degrees Celsius, whereas whereas the bright side is about 2400, so almost 1000 degrees more. And because of this gradient and because of the really strong winds, there's a lot of circulation and a lot of really strong wind that can even be measured in terms of speed. And because I was really curious to find out how exactly did the scientists actually figure all of this out, which by the way you can also do by reading the paper in the description below, I wanted to give you a brief summary of what they did. So essentially, by using this really sensitive instrument, they looked at the planet that orbits around the star and were able to detect that when the star is at this angle and we're looking from over here, we only seem to see a little bit of iron coming out from the so-called leading edge. But interestingly, the transmission here was a little bit different because the iron was basically not moving anywhere. In other words, because the planet is spinning this way, and because the iron seems to be spreading from this really hot point, the average velocity was around 0 kilometers per second. When they looked at the second point, where basically the planet is right in front of the star, there was practically no observation of any iron at all. And then, when they looked at it from the third angle, when the planet turns a little bit, they were able to see a lot of different iron emissions, and this time the velocity was about 11 kilometers per second. So basically the iron was moving really fast to the dark side of the planet, and these very large emissions suggested that iron was precipitating and creating a lot of, well, basically rain. So all of these observations suggest that this type of a planet has very unique and very unusual features. It has this very unusual super hot spot where iron seems to disintegrate into atoms and thus become a somewhat unusual cloud formation of superheated iron that most likely covers a very large part of the planet. And then, as we move closer and closer to the dark side where it's a little bit cooler, that's when we get the superheated rain of iron as well. Now, what happens to this iron afterwards is currently unknown, but I guess we can imagine that it probably precipitates and becomes some sort of a very large liquid ocean of iron as well. Although eventually, if it does reach the dark side of the planet, it probably then solidifies and becomes just chunks of iron. But for the scientists studying these planets, the biggest discovery here is the chemical difference between the day side and the night side. It seems that some of these planets possess completely different chemistry on two sides. It's as if you had two different planets, one on this side and one on the other. So it's kind of like combining, for example, half of planet Earth with something more unusual like Venus and then turning it into a single planet, with one side being extremely hot and one side being much cooler and both having very different chemical composition. And the instruments that they use for this so-called espresso just recently started operating. And this is an extremely accurate and also relatively brand new planet hunting telescope that will very likely lead to incredible new discoveries in the next few years. And so thanks to all of the upgrades with the European Space Observatory, we're going to be seeing and hearing more about these unusual planets in the next few years for sure. But discovering this planet, or technically analyzing this planet, also allowed us to understand that these planets do have clouds. It's just not really clouds that we thought they would have. Here they seem to possess clouds that we would never really expect to see anywhere in our own solar system. Clouds of extreme components such as metals and other unusual elements that are typically solid here on Earth. But unfortunately, because of the distances, which is 390 light years away from us, we're not really going to be going here anytime soon. The only thing we can do is try to study this planet a little bit more just by observing it for now, until we learn how to travel faster than the speed of light, which by the way is still kind of impossible. But you never know, we might find a way to kind of cheat the system. Hello wonderful person, this is Anton, and in this video we're going to be talking about a very recent discovery of a pretty amazing FRB, also known as fast radio burst, that seems to be very different from everything else we've seen so far. Now honestly, I was pretty excited to find out something new about the mysterious FRBs that we've been seeing for pretty much the past 13 to 14 years. It's still kind of a mystery to us, we still have no idea what they are. And even though we've been seeing them pretty much everywhere around the night skies, we can't really explain them just yet. If this is your first time hearing about so-called FRBs or fast radio bursts, they are literally what they sound like. They're very fast, and they're sort of like a burst of radio energy that can only be seen in certain frequencies. And for the most part, they're really fast. They only last for like a few milliseconds, so it would be almost impossible to catch them with a typical handheld radio. You would have to use a very specialized radio telescope in order to record the actual bursts happening in real time. Which is why it took us so long to actually detect them for the first time ever. The technology wasn't there yet. Now, we don't really know what causes them, and for most of them, we don't even know where they came from. but in most cases, really far away. We're talking about distances of billions of light years. And also they all seem to be somewhat different. Some of them are really short, some of them are a little bit longer, some of them are louder than others, and some of them are repeatable and have been seen more than once from the same location. Although up to now, none of them had any patterns. And when it comes to trying to explain what's causing them, well, there are a few ideas. One of them is, of course, some sort of interaction with a pulsar or a neutron star that's causing some sort of a very unusual effect that we're seeing from a distance. Some scientists have even suggested that maybe it's related to some sort of a collision between two stars, and instead of a supernova, it produces a fast radio burst and could potentially explain what we're seeing. Simply because it has to be a really powerful event for us to see these radio bursts from such a far away distance. On the other hand, some of the theories propose that all of these effects were coming from the very powerful and very mysterious magnetars, which I've discussed in many previous videos. These are also neutron stars, but slightly different from a typical pulsar. At the same time, some scientists suggested that maybe it's an effect of a very fast spinning star. But all of this so far is not really satisfactory, and obviously the idea of aliens communicating with each other came up once or twice as well. But so far, none of these ideas really explain everything we're observing. First of all, some of these FRBs are not repetitive, meaning that a spinning star would not really explain it really well. They also seem to have slightly different features and are coming from very different galaxies, while at the same time not really possessing any features of, for example, a typical neutron star. But this new paper that just came out only a few days ago from when I'm making this video might finally help us resolve what's really happening here. Because for the first time ever, the Canadian scientists discovered that one of these FRBs has a very predictable pattern and seems to actually reoccur every 16 or so days. In other words, it has a very well-defined phase of roughly around 16 days per cycle. And this is something we've never seen before. They actually observed this unusual fast radio burst over 400 times over a period of several years, and in that period they discovered that the 16-day cycle was more or less easily predictable. Now, of all of the previous FRBs we've found, only some of them, I believe 10 or so, were actually repeatable. The rest only happened once. But of all of the ones discovered, only this one right here seems to be the one with the actual predictable pattern. All of the other ones happened once or twice or maybe several times, but there was no pattern whatsoever. And because of this discovery, we're now a little bit closer to maybe finally solving the mystery of what's really causing these unusual flashes. But once again, not really aliens at all. As a matter of fact, even if you look at these predictable patterns, it's still quite obvious that these are natural signals. They're not really all exactly the same. They always have a slightly different appearance. And so these signals can only be produced by very likely a repetitive but natural source. In other words, these have no sign of artificial intelligence or some sort of artificial communication. And interestingly, these signals seem to arrive pretty much every single hour for about 4 days straight and then disappear for about 16 days. And then come back again for another 4 days, which is really strange. It's really difficult to explain right now what could cause such an unusual pattern. And one of the possible explanations here is, or are, two celestial bodies, with an orbit of roughly around 16 days around one another. And during those 4 days where we see the signals, something probably happens and somehow manages to produce these really powerful radio signals that are visible from Earth. And then during the next 16 days, we don't get to see them because the bodies are not aligned toward our planet. So we're not entirely sure exactly what's happening here, but that's because we just don't have a theory yet, which actually reminds me of how we discovered neutron stars, or technically pulsars, and how back then people were also kind of not sure what they were, and most importantly there was a lot of talk about extraterrestrials. The idea of a pulsar or a neutron star that sends out energy and can be seen from really far away was actually very theoretical. Even back in the 30s, the scientists already believed that neutron stars could potentially exist. By the 60s, they already had actual theories formed on how we could potentially see neutron stars and how they could produce these unusual jets that you see right here on the screen. So all of this was already predicted theoretically, we just had to see them, but we didn't have the technology. The telescopes were just not as advanced yet. Until 1967, when the brilliant Jocelyn Bell burner was able to finally detect the first ever pulsar. Here's the original observation from 1967, and essentially within only a few weeks they were able to connect the observation to the available theories once and for all confirming that the neutron stars and pulsars do exist, and this is exactly what they're observing. But prior to this, for I guess a few days at least, they actually refer to this as LGM, or Little Green Man, because when they just discovered it, they didn't really know what they were looking at, and it looked like a communication from an alien species. Which is kind of where we find ourselves right now with the FRBs as well. But the only problem here, or the main difference here, is that we don't have the theories to explain any of this. So in other words, we've almost reached something opposite of what it was like in the 60s. Our technology is really advanced, we can see things that were totally invisible to us before, something we could never even imagine, but the theories fell behind, and it's very difficult for us to establish what's causing this. And I think one of the major differences or major difficulties for modern astrophysicists is that, well, there are so many papers coming out every single day that it's become almost impossible for anyone to actually catch up with everything that's being released. So trying to identify the exact explanation here would be quite a challenge. Now, luckily for us, this particular burst came from the closest galaxy to us, and also a galaxy that's surprisingly similar to the Milky Way. Here's actually what this image looks like in real life, and as you can see, it's somewhat similar in shape to Milky Way galaxy, and because of its proximity, we could even find a way to study it in a little bit more detail. The distance here is approximately 500 million light years away from us, which is way closer than anything else, even though it does sound pretty far away. Nevertheless, this is right now our best chance to try to once and for all solve the mystery of FRBs by looking at them with everything we have and trying to discover what exactly is happening out there. Now, the way that the Canadian scientists were able to discover and also analyze this particular FRB is by using the amazing Canadian CHIME telescope, which honestly doesn't even look like a telescope at all, but it is a very powerful radio telescope that only became operational a few years ago and actually is eventually expected to discover up to several of FRBs per day. It's super sensitive and is able to detect things we could never detect before. And thanks to CHIME, and I think that stands for Canadian Hydrogen Intensity Mapping Experiment? I might have gotten this wrong. But anyway, thanks to CHIME, we'll hopefully within the next few years be able to finally resolve the mystery of these FRBs. Now, as I mentioned before, the chance of this being some sort of alien technology or some sort of extraterrestrial activity is practically null. There's almost no way that this is something artificial. But the chance of this being some sort of a natural, never before seen phenomenon that could in some way help us discover something we've never known before about, I don't know, neutron stars, black holes, maybe things like quark stars, is very high. This is probably something we just can't really imagine right now, and we need a theory to try to explain what we're looking at. And just like with black holes, neutron stars, pulsars and so on, whoever is able to explain it will very likely end up with a Nobel Prize. But until we get a better idea of what exactly this is, what's causing it, where it came from, why do some of these repeat and some don't, and are they all kind of similar in some way, I guess that's about it. But before I finish, I also wanted to thank this wonderful person whose name I think I can't really pronounce, but I think this person is from Turkey, and he initially sent me the article about this. And even though I did see the paper originally, it didn't really seem important until I read the article. And so thanks to him, I was able to cover this pretty quickly. And anyway, in case you didn't know, one of the best ways to reach me is actually on Twitter. I use it a lot more than other social media. As a matter of fact, I almost entirely stopped using Facebook now because it just got out of control. But I also do my best to try to reply to as many comments on YouTube as I can, so if I didn't get to your comment, I'm sorry, but I'll try next time. Hello wonderful person, this is Anton, and in this video we're going to be talking about a discovery of a new exoplanet, a planet somewhere out there in the galaxy, but using a very original method we've never used before. And this could allow us to discover a lot more planets out there. So as of today, we've confirmed over 4,100 different exoplanets, including of course the most likely biggest discovery to date, the system known as TRAPPIST-1, with 7 different terrestrial or Earth-sized exoplanets orbiting around it, several of which are in the habitable zone. But there are a lot of exoplanets that are very different from anything we have in the solar system. However, there are things we can learn from the solar system in order for us to discover these unusual planets. And back in the 1960s, the scientists looking at Jupiter discovered something very unusual about it. They were witnessing these unusual radio waves, radio emissions, and these emissions were surprisingly in sync with one of its moons, the closest large moon known as Io, This is also the most volcanically active moon in the solar system and has quite a lot of really interesting things happening on the surface here. As you can see, it's filled with various lava plains and also has a somewhat thin atmosphere produced by the volcanic emissions that actually does interact with Jupiter itself. But why is it that there were these radio waves coming from the system, and what exactly was happening here? Well, it took some time, it took a few decades actually to try to understand what's happening here, but finally the scientists were able to explain this. Now, what's really important to understand here is that these radio emissions are really powerful. They're actually as bright in our night skies as the radio emissions coming from our own sun. So this was something that was quite intriguing, and the scientists were waiting for a few probes to get here in order to find out what's really happening. Well, after a few probes that visited this system, specifically the Voyager probes and the Pioneer probes, scientists were finally able to answer what's happening here. Turns out, as the volcanoes erupt on Io, they release quite a lot of gas that eventually kind of settles around the planet, creating this atmosphere that then releases certain electrons. And these electrons can then start interacting with the magnetic field of Jupiter itself. So this is like having a negative charge move around the magnetic field, which will then generate current. But here, this current will then transfer toward the magnetic poles of Jupiter, and this will generate quite a lot of wave activity. These waves are not very powerful, but right at the actual poles, when they actually kind of merge all together, it does generate a relatively powerful emission, almost like a laser-like emission that can be seen from really far away, including of course Earth. And this is what we were witnessing for so many years, and this is how the mystery was resolved. And what's really important here is that these emissions, depending on the frequency and depending on the actual power, will also tell us quite a lot about the actual planet itself. In other words, by reading the frequency and the power of these emissions, we can learn a lot about the planet and also the moon itself, and thus analyze them remotely by just getting these signals. And it just so happens that the brilliant scientists from Netherlands, using the so-called LOFAR, or essentially a series of radio telescopes that are quite powerful to detect really weak signals from really far away, were able to detect an unusual signal coming from this system right here, known as Jayjay 1151. And as you can see, it's located in the Ursa Major constellation. And as you probably guessed, it's essentially a very similar type of a signal we'll get from Io as well. So it's kind of like a laser-like radio emissions in around 150 MHz of frequency. As always, you can learn more about the actual discovery and the study in the description below. And so, using approximately 20,000 different radio antennae that were all connected in this system, these scientists were able to discover that this system, known as Jayjay 1151, had an Earth-like planet, or at least Earth-sized planet, orbiting the star anywhere from 1 to possibly 5 days. It's still not really accurate in predicting the actual orbit, but as we discover more and more of these planets, I'm sure this technique will be refined and become a lot more accurate. Right now though, just discovering this planet using this method is really incredible. And essentially how they found it was by looking at the interactions of the aurora, the so-called northern and southern lights. These aurora will always produce an extremely powerful radio emission, and this radio emission will very likely be visible from really far away. And because of the success of this technique around Jayjay 1151, these scientists believe that they'll be able to discover a lot more of these exoplanets in various other systems as well. But you do need to have a very specific type of a star and a very specific system. Now, in our case, in the solar system, the sun is really far away from every major planet, so there is no actual star-planet interaction. In other words, because our sun is not particularly powerful magnetically, and because our planets are much farther away, more specifically this far away, this is where Earth would really be in comparison to the sun, and here's how this compares to the previous orbit. All of this means that there is really no way to detect Earth or any other planet from outside of the solar system using this technique. However, other star systems, such as of course TRAPPIST-1, are extremely magnetic. This star here is a lot more magnetically powerful than our sun is, and the planets here do experience a lot of star-planet interaction. We're still not entirely sure how any of this affects these planets. They might actually become extremely dangerous to live on, but we do understand that because of this interaction and because of the way that the aurora are generated, it's very likely that pretty much most of these planets will produce these very powerful radio emissions. And most importantly, using this technique we'll also be able to even find planets in the habitable zone of various red dwarfs. So in this case, because the orbits here will probably take maybe around 5, 6 or 7 days in the habitable part of the star system, and in case of TRAPPIST-1e it takes it about 6 days to go once around the star, this definitely creates a very good opportunity for us to discover a lot of various habitable planets around red dwarfs that would be invisible to us otherwise. And all of this simply because the star itself will very likely have very powerful aurora that's definitely going to produce a lot of radio emissions, really powerful radio emissions visible from pretty much everywhere in the galaxy. And since red dwarfs are the most common types of stars in the galaxy, this is probably going to be an extremely easy way for us to discover a lot of exoplanets out there. Unfortunately though, because these planets are producing so many radio signals and because they're essentially interacting with the star itself, we don't really think they will be habitable to humans. They are nevertheless going to be really interesting for research purposes. And also because the closest planet to us, Proxima Centauri, is also a very similar planet to the one discovered, it's probably going to be a very interesting way for us to discover more about it. If we try to listen to these radio signals, we might be able to learn a lot more about the closest planet to us. And as we learn more about aurora on Jupiter and of course aurora on our own planet Earth, we'll definitely be able to answer even more questions about these exoplanets, simply because by studying our own aurora we'll be able to understand what's happening here as well. But there's one thing I need to mention though. This study is still only the first such study and we still need to confirm their discovery. More specifically, we need to use other methods to confirm if this planet even exists or if something completely different is happening here in order to cause these unusual observations. Either way, I'm sure in the next year someone will either confirm or disprove this idea, and if this is correct, then we'll definitely be able to discover a lot more really awesome exoplanets out there. More importantly, this will allow us to see and detect even closer exoplanets around nearby systems. There are a lot of red dwarfs near us, and finding planets around them would be quite interesting. Hello wonderful person, this is Anton, and in this video we're going to be talking about the mysterious dark matter once again. Although, actually not the dark matter, but the opposite of that. One of the theories that tries to remove dark matter from existence completely and instead focus on trying to understand the universe without needing any dark matter in it whatsoever. So first of all, this is the paper. You can find this in the description below, and the main idea in this paper is that for the first time ever, the scientists studying so-called MOND, or the modified Newtonian dynamics, have been able to partially recreate part of the universe using the parameters from the MOND theory, and it surprisingly looked somewhat similar to what we really have in what we see in our universe. Now let me explain this in a little bit more detail, but before I explain this to you, I wanted to focus on why we still believe dark matter might exist. So originally, some of the first scientific papers about dark matter were actually made by this wonderful lady, this is Vera Rubin, who was the first to notice something unusual about the so-called galactic curves. In other words, she noticed that when we look at different galaxies, even though technically if we use Newtonian physics, we expect some of the farther stars here to move slower. Basically, the farther away they are from the center, the slower they should move, just like planets. In reality, we saw something like this. The velocity was much higher than we expected. 10 times higher as a matter of fact. And this was the first official confirmation of the possible existence of this so-called dark matter. But over a few decades now, we've collected a lot of other evidence as well. Like for example, there are these unusual gravitational lensing effects coming from what seems to be empty space. And some of these gravitational lenses are extremely powerful, and this would be very difficult to explain with just the visible matter. We've also noticed that there are quite a lot of these so-called dark matter galaxies, or essentially galaxies that have some stars, a few visible stars, but for the most part they actually behave like a typical galaxy. The stars here move pretty fast, suggesting that something is holding them together. We've also seen various interactions in galactic clusters, and I think the most famous one, and the one that's usually used to prove dark matter, is the so-called bullet cluster, where several galaxies collided, and we've observed the interaction between regular matter and what appears to be this unusual invisible matter as well. And all of these effects to us, to modern scientists, suggest that dark matter might be a real thing. There are actually a few more examples as well. I'm not going to mention all of them in this video, and I've also mentioned some of them in previous videos, but the idea is there. But the problem is, for the past, I guess a few decades now, all of our attempts of finding dark matter using relatively expensive experiments have not really been successful. There were some partial successes, but nothing where you can totally say that we've just discovered it. Which is why many alternative theories have been proposed over the years, and the one that's probably most accepted today, the one that's sort of alternative and not too crazy, is what's known as MOND. Modified Newtonian dynamics, originally proposed by this person right here, Mordechai Milgram, who essentially suggested that we could actually explain these observations if we redefine the way gravity works at faraway distances. In other words, he suggested that even though for a typical galaxy close to the center, you'll still observe Newtonian effects, as you move away from the center, the farther away you get, the more unusual the effects get. And the way that this theory works in a nutshell is, well, it explains the Newtonian physics or Newtonian attraction between two bodies by involving distance as well, but in a very different way. In other words, up to a certain distance, the attraction between various bodies is relatively similar, but as you move away from the center of the galaxy and the acceleration becomes lower, such as here in the outskirts of a typical galaxy, the attraction between bodies becomes considerably stronger, explaining why galaxies don't fall apart even when stars move this fast. In other words, it reinterprets the gravitation formula for faraway distances. And this is something that does explain a lot of things in the universe, including, of course, the previously mentioned galactic curves. But the biggest thing that it could not explain is the creation of the universe itself before. Basically, all of our modern computer simulations using supercomputers are always able to simulate relatively accurate galactic representations. This is basically what's known as universe in a box, using the theory that accepts dark matter, also known as lambda CDM model. This is the model where we think dark matter exists. And basically this is the most accepted theory right now. So for example, in this project here, this is known as the Illustris project, the actual galaxies generated are extremely accurate, but this does use dark matter. We've never before been able to do this with other theories. But this paper, for the first time ever, was able to generate this universe in a box, but using no dark matter. And according to the scientists, it's more or less correct. It's more or less something that we can compare to the real thing. Which is great news for the scientists that don't believe in dark matter and think that the MOND model explains it a lot better. Now, it obviously still doesn't explain some of the other things we're seeing, like for example, the previously mentioned bullet cluster that you see here is still kind of difficult to explain, or actually impossible to explain using the MOND model. And also some of the other effects, like the gravitational lensing effects, are also not particularly MOND friendly, but nevertheless, this new simulation definitely is a great step for possibly explaining the universe without the need for dark matter. Now, the takeaway message here is not that dark matter does not exist. It's just sort of a new explanation to how we can see the universe differently. And despite the success of this new simulation, we still need to work out a lot of other problems that the model has. But according to the scientists behind this paper, some of the things simulated in their model was even better than in the traditional dark matter model. Like for example, they were able to generate clusters that were a little bit more realistic, while at the same time their model was also able to generate quite a lot of various galactic disks, like the one you see here, and the one that's very similar to the Milky Way in a sense. And this is something that's not usually that easy for other models. While at the same time, the scientists also mentioned that for the most part, when the simulations use dark matter in them, these results are normally very sensitive to the location and the number of different supernovae. So in some situations, not a very realistic galaxy is created if the supernova numbers are incorrect. And in the MOND model, it didn't really matter as much. But nevertheless, there are still some major problems with this as well. One of the biggest problems here is that according to the MOND model, the speed of light and the speed of gravity is not exactly the same. But since 2017, when we started measuring gravitational waves, we discovered that both speed of light and speed of gravity are actually the same. So in that sense, MOND model is not really correct. At the same time, certain motions of globular clusters are not easily explained by MOND model either. As a matter of fact, they're usually predicted incorrectly, whereas globular clusters we see in reality do seem to follow a more lambda CDM-like motion. In other words, the dark matter motion. So in that sense, there are still a lot of questions to be answered for both of the theories. Or technically, it's not even a theory yet, it's just a hypothesis. And neither of these theories can be disregarded or disproved very easily. They both have quite a lot of interesting ideas that are quite supported by various scientists. As a matter of fact, Vera Rubin herself, who passed away only a few years ago, started speculating near the end of her life that maybe we need to redefine how we see Newtonian gravity. So in a sense, she believed in a kind of a Mond-like model and slowly moved away from believing in dark matter as an actual particle. Most of this came from the fact that over the decades they kept predicting that we're gonna find dark matter at some point, but nothing was coming out of it. So something else was happening with the universe that we just didn't understand just yet. But in all honesty, what I personally think is that neither one of these models is perfect just yet, and neither one of these explains things the way they really are. There's probably something else happening here, we're still not really sure what, but discovering these things is going to be one of the biggest groundbreaking discoveries of the 21st century, hopefully. I mean, hopefully we discover what's happening here, because, I mean, it's been driving a lot of scientists pretty crazy. And because even today we have so many experiments already running and so many more that are planned for the future, I'm sure in the next 30 to 40 years we'll finally be able to solve this mystery. At this moment, I'm personally not even sure what it is anymore, but because none of the theories provides an absolutely perfect answer, this is why it's a little bit difficult to say with certainty. Which is of course where we go back to the original idea of scientific process. We have to get enough evidence to support our idea before it becomes a fact. Right now, none of this is factual. But hopefully in our lifetime we'll be able to explain what's going on. Otherwise, a lot of people are just going to be very dissatisfied. Anyway, on that note, once we discover more, I'll make sure to follow this up with another video, but for now you can check out the paper that I mentioned in the description below, and some of the pictures from the simulation are available in it as well. And before we finish, well, it's very unfortunate that Vera Rubin passed away without ever winning a Nobel Prize, and many people believe that she definitely deserved it, but a few months ago, to commemorate her name, this beautiful observatory was renamed into Vera C. Rubin Observatory. This is actually an amazing device that's going to help us understand the universe in a lot more detail. And in the next few years we'll be hearing a lot more about this particular observatory because it's going to be making a lot of new discoveries. Hello wonderful person, this is Anton, and in this video we're going to be talking about a very fascinating topic of Quasar Tsunamis. And that does sound like something extremely powerful and extremely dangerous. So honestly, quasars are always fun to talk about, mostly because they're still quite mysterious. Because you know, from I guess a few decades ago when we originally saw them as these really bright stars and we couldn't really figure out what they were, to the discovery that they're extremely powerful and extremely massive galaxies, which a lot of scientists didn't even believe at first, to then discovering that a lot of this power comes from these ultra-massive black holes in the middle that are absorbing so much mass that they produce a tremendous amount of energy and essentially this blinding light that creates brightness that's brighter than approximately 1,000 galaxies combined together. While at the same time, with so many different quasars out there, we're always kind of fascinated about different connections between them, what they actually represent for the evolution of the universe itself, and the more important question here is in regards to how this evolution of galaxies may have influenced our own galaxy as well. So in other words, has our own Milky Way been a quasar at some point in the past, and what did this do to our galaxy? And as we learn more about them by looking around the universe and discovering more of these quasars and the interaction they have with the galaxy itself where they reside, we realize how extremely powerful these events or these things, these objects are, and how they actually do influence not just the galaxy where they reside, but everything around them as well. Not to mention, we've also been discovering all sorts of connections between the, for example, galactic web or cosmic web and the position of quasars across the universe. So there's definitely a lot of really interesting things when it comes to quasars. It's one of the most fascinating studies in cosmology. But this recent paper that came out only a few weeks ago talks about something else that we kind of expected, but never really to that extent. And specifically here we're talking about what's known as a quasar tsunami. And as you can probably imagine, just like as scary as it sounds, it's something extremely powerful and something that does influence the entire galaxy dramatically. Now quickly, in a nutshell, so a quasar is essentially an extremely hungry galaxy, or technically galactic nucleus. The center of this galaxy usually possesses an extremely powerful black hole that starts eating up so much matter that it essentially just explodes with energy. It starts producing so much energy that it generates these really powerful winds that influence the rest of the galaxy as it keeps absorbing more and more matter. But as the matter falls into the black hole and generates a lot of this energy that's then exposed, this so-called galactic wind, or I guess you can call it quasar wind, becomes so powerful that it actually starts to influence the rest of the galaxy, in most cases causing a lot of the star formation to completely stop. Now this is something we kind of expected, but the recent paper used Hubble telescope to analyze 13 different quasars and discovered that some of these quasars are so powerful that they go beyond disabling stars. They create conditions that are essentially really extreme. For example, they generate such powerful winds that the material from within the center starts moving at approximately 6% of the speed of light and moves across the galaxy, colliding with everything on the way, first generating a lot of X-rays and a lot of ionizing UV radiation, essentially radiation that would probably strip any planet of atmosphere, and then slowly transforms into visible light and even infrared light. So essentially it creates this kind of a firework of different frequencies that are visible from really far away, and all of this is huge. It's the size of a whole galaxy. It's at least several thousand light years across. So it's almost the size of some of the smaller galaxies. They've also witnessed one of the quasars exhibiting a tremendous increase in energy that actually accelerated the wind by about 6 to 7%. So essentially it was moving at about 6% of the speed of light, and then the speed of this wind increased by about 3 million miles per hour, or about 4.5 million kilometers per hour. All of this within relatively short time frame. So this is something that we really didn't expect to see. This is how extremely powerful quasars and these active galactic nuclei are in general. So they do produce tremendous amounts of energy that influence the rest of the galaxy. And so by observing different quasars, they've established that there were a lot of different effects here. A lot of really strong and powerful winds, essentially causing the entire galaxy to kind of expand and inflate in some sense. And this is literally why the scientists behind this paper called this a Quasar Tsunami. It was a huge wave of really powerful, extremely high in energy material that was moving across the entire galaxy, slowly pushing everything aside, slowly destroying everything on its way, or at least influencing a lot of these stars in such a way that no new star could be produced, and very likely a lot of planets would probably be completely stripped of everything. And it seems that a single quasar, similar to the ones they've looked at, usually can easily push out approximately several hundreds masses of the sun every single year, and a lot of this mass ends up being in the intergalactic space. Now some of it might actually eventually come back to the galaxy, which is what we believe happens in most cases. In other words, some of this gas will kind of move away and then slowly get attracted back to the galaxy and then re-enter and possibly create new stars afterwards. But some of this gas might also end up in the intergalactic web, in the cosmic web, and be trapped there forever. So we're not really sure how all of this really influences galaxies, but it does explain why we don't usually see large massive galaxies as often as we would like. We do see a lot of smaller galaxies, and in most cases there is actually a correlation between the mass of the central black hole and the size of the galaxy. So what this all means is that the actual black hole in the middle controls the size of the galaxy. It actually prevents certain galaxies from growing too large, and also prevents some galaxies from having too many stars. And the more active the black hole becomes, the larger it gets, the more likely the galaxy is not really going to possess too many stars and too much mass. Most of it will probably get expelled. At the same time, this also explains why in most cases we see that star formation happens in bursts and usually around the same time. Like for example in the Milky Way, we know that these bursts created most of the stars. The vast majority of other stars, there were only very few stars that were created in the Milky Way galaxy in between these bursts. Now, we think our sun was actually also produced during such bursts, but for the most part, we never really understood what's really stopping these bursts from happening more frequently. And these scientists and a lot of other scientists suggest that it's actually the active galactic nuclei. Now, we don't think our Milky Way has ever really been a powerful quasar, But we do know that there were a few cases or a few times when our galaxy did experience the active galactic nuclear bursts. More specifically, not so long ago we discovered these so-called Fermi Bubbles, which seem to be the leftovers from one such experience when the black hole in the middle of our galaxy started absorbing a lot of mass and created these really large and powerful emissions. Now, it may have not really been a true quasar, or at least not a quasar that would be really bright as some of the ones we've just observed, but it might have been enough for it to kind of look like this, like a typical quasar from a distance, while at the same time, it did probably stop a lot of the star formation in the galaxy for at least some time. But we haven't really experienced any major bursts since then, and this was probably a few million years ago. So we don't really know what causes these bursts to occur afterwards. This is yet another mystery of the universe. Or we don't actually know what causes stars to suddenly start forming in between these galactic bursts. Or we don't actually know or currently understand what causes sudden bursts of star formation in between these very powerful galactic bursts caused by black holes. But it is something we would really like to learn more about, because technically, if such an event occurs in the Milky Way galaxy, there is a really high chance it's not really going to make our Earth any more habitable. So these events are really important for us to understand and for us to actually learn about, especially because in the last few years we've discovered that our own black hole in the middle of our galaxy seems to be getting a little bit hungrier. It's been increasing in brightness over the past few years, and we can't really explain why just yet. So we're secretly hoping that this is not the beginning of some sort of a major quasar event or any other event that could potentially cause problems for humanity. Although currently we don't really think that anything like this is going to happen anytime soon. There are just no signs or no evidence to suggest that our galaxy is going to become a quasar anytime soon. But this doesn't mean that we should stop learning about quasars. This nevertheless is a very fascinating topic and does teach us a lot more about the universe in general. Hello wonderful person, this is Anton, and what happens when you collide two planets? We generally have a pretty good idea, and we have a lot of simulations that allow us to imagine such an event. But what happens when a planet collides with a star? Now that's a completely different question, and in this video we're going to be investigating the effects and possible observations of such events. So let's start right here. This is known as WASP-12b. Today it's known as the darkest planet in the universe, simply because this is the darkest planet we've discovered so far. It's been compared to charcoal dark, or essentially absorbing about 94% of light, and this is maybe what it kind of looks like if you were to look at it from a distance. This is compared to our own Jupiter. At the same time, some other simulations suggest that it may also kind of look like this, a kind of a egg-shaped planet because of all of the stretching it received from its parent star. And this is what it also looks like in some of the modern NASA simulations, basically an egg-shaped planet. But this is not the only things that we've discovered about this unusual planet. Recently, the scientists studying this planet discovered that it's slowly moving closer and closer to its parent star, and they were able to calculate by how much. Now this is something we obviously expect, because if a planet is this close to the parent star, it's probably going to at some point fall into the star. And even though this was speculated before, and we obviously predicted these events to happen, we didn't really know until now by how much these planets move towards stars. And even though a single orbit currently takes roughly around 1 day, it also is decreasing by about 29 milliseconds every single year, meaning that within about 3 million years from today, it's going to collide with a star. But this is where the mystery begins. As of today, we don't really know what exactly happens when planets do collide with stars. We think that these events are pretty common. We actually think that at least one planetary collision occurs in the entire galaxy every 2 years. But the thing is, obviously they're a lot more difficult to detect, and some of the planets are just too small for us to see any effects. But if a gas giant collides with a star, that's a different story. So if a hot Jupiter collides with a star, it's very likely going to produce major effects. And there's a very likely chance that we've seen this happen a few years ago. So let me briefly talk about a star known as V838 in the constellation of Monoceros. This very large, very massive and very bright B-type star was kind of not really well known to us because it's pretty far away. It's about 20,000 light years away from us. But starting in 2002 and lasting for a few years, it became one of the most famous objects, creating one of the most beautiful effects we've ever seen. And this is the effect I'm talking about. This was actually filmed over the period of several years, it created this absolutely gorgeous, beautiful cloud that didn't really look like any other nebula or supernova, and we couldn't really easily explain how this acquired such a shape or how all of this was happening. Initially, some of the scientists thought that this is a type of a nova when basically a nuclear reaction occurs around a white dwarf, but we realized that there was no white dwarf here and it was a B-type star. So some scientists started speculating that maybe this was actually a collision between two stars, or maybe this was a collision between a star and a planet. And both of these in some sense make sense. If this was a star-star collision, then the larger object was probably around 8 masses of the Sun, while the smaller object here was about 0.3 masses of the Sun. So it was a collision between a B-type and a red dwarf. Now, in this simulation, it's very likely going to just create a supernova. We're not going to really see anything as beautiful as you just saw from the actual images that we took. But nevertheless, this gives you an idea that these events could occur and we may have witnessed one. But at the same time, many scientists don't think that this was a star-star collision. Some scientists think that this was actually our first observation of exactly what we were predicting is going to happen around WASP-12b. Essentially, a hot Jupiter slowly making its way toward the star and then colliding with it. And even though in this simulation only a very little explosion was created on the surface, in reality, V838 for a very brief period of time became the largest star in the galaxy. It expanded dramatically. Just to give you a solar system comparison, it's as if our sun expanded to be... Okay, this is actually going to take a while. I'm gonna have to start increasing its size by a lot here, and you can see that it already actually changes properties, but it's going to end up swallowing the entire solar system, because its total radius was about 1500 astronomical units. That is about 50 times as far away as Neptune is from the center of our solar system. And then slowly it started shrinking. So it went from being about 1,000,000 degrees to only about 15,000 degrees, and also size of Betelgeuse by 2014. So it took it about 12 years to suddenly shrink to be comparable in size to Betelgeuse right here. And it still is probably shrinking even today, but the initial explosion, as you can see, produced a tremendous amount of various materials just being completely thrown out of the system. This cloud is going to stay there for a very long time, and it's going to be really beautiful even in the years to come. Today it actually kind of looks like this. This is a more modern picture, but it's still going to transform for many years. And since this star is actually relatively young, it's only about 4 million years old, it probably did experience some sort of initial collision either with its partner star or a planet. But if it was a planet, it had to be a very large, very massive planet, very similar to a lot of these hot Jupiters we've been observing pretty much everywhere around our galaxy. And WASP-12b could be this next candidate for such a very tremendous explosion. But why was this cloud even created? How could this even be possible from a typical planet? Well, the models today suggest that when a typical planet comes closer and closer to its parent star, at some point, if it's a gas giant that has a lot of hydrogen on the inside, this hydrogen starts creating deuterium, which is a typical isotope of hydrogen. And then deuterium begins its fusion and creates a tremendous amount of energy, which leads to the sudden expansion of the planet, and as it keeps increasing in size and sort of expanding, this ends up producing even more deuterium and thus even more expansion. And at some point this becomes such a fast reaction that the entire planet kind of just bubbles up and, I guess, in some sense explodes. So it's almost like a very unique runaway nuclear reaction that explodes the planet, creating this extremely bright and very powerful cloud that can be seen from really far away everywhere in the galaxy. But this most likely takes a very special kind of a planet, and it also probably only happens around stars that don't get a chance to break up this planet into little pieces and into a kind of a ring around themselves. So essentially the planet has to stay as one piece and then somehow approach the planet to initiate this reaction. Because normally, if I were to just place a planet here in the orbit around the star, not only would it evaporate, but it would also start falling apart, creating a kind of a fragmented ring here, which would very likely not create these explosions. So very special conditions have to be reached for this to actually occur. And what this means for the darkest planet in the galaxy, for WASP-12b, is that it's very likely at some point going to become this type of an explosion as well. Assuming, of course, we're correct about the origins of this cloud right here. If, however, this was a star-star collision, we might not be able to see this for a while. Yet, if it's a hot Jupiter to star collision, we're probably going to see one within the next few decades, or possibly even sooner than that. In other words, these large planet-to-star collisions could be a lot more common than we thought. But a lot more investigations are needed, and a lot more studies need to be done on exactly what we think might happen if a typical gas giant falls into a star. But the bigger question here is, of course, has this happened in the solar system? It's very likely we did have unusual planets in the solar system that fell into the star, at least in the beginning of the formation of the solar system. But if something similar to this was generated when the solar system was only 4 million years old, how did everything else stay in orbit? Did this have some sort of a profound effect on the formation of the planets, or did it just not happen at all? So this is something we need to investigate in order for us to understand a little bit better what made our solar system the way it is, and how we came to be here as well. So I guess one day maybe we'll discover the answers to these questions, but maybe also this will remain a mystery for a very long time. So obviously there are quite a lot of really unusual and strange stars and exoplanets we've discovered in the last few decades. But we seem to be discovering more and more unusual stars, and with every single discovery we're learning so much more about our own solar system and of course about our own galaxy as well. This, for example, is a very recent discovery of two stars, a binary system, with two stars essentially forcing each other to throw off their own envelopes, creating this beautiful image you see on the screen. This was only discovered a few weeks ago. But today we're going to be talking about another unusual discovery, a star that pulsates, but only on a single side of the actual surface, basically only here. But first, briefly about star pulsations. So first of all, almost every, and I would even say every star out there pulsates to some extent. For example, this right here is a typical Cepheid variable. Specifically, this is known as a delta Cepheid. And this is sort of what the star would look like if you were to come really close to it. Essentially, it's a star that, I guess in some sense, looks like it's breathing. It shrinks and then it grows, it shrinks and it grows. It does so extremely predictably, and this pulsation even depends on its total mass and involves the top brightness, which in a nutshell means that we can use these stars as a kind of a distance candle to measure distances across the galaxy and the universe, which is exactly what we use Cepheid variables for. The most famous Cepheid variable is the star known as Polaris, also sometimes referred to as the Northern Star, and this is essentially what allowed us to learn so much about them. This star also pulsates, and because of its very regular pulsations and its total brightness, we can use this star and other stars to predict distances across the galaxy. Some stars, however, and actually most stars, are not as predictable. This is from Betelgeuse. The actual pulsating here is very unpredictable, and as we've been learning over the past few months, Betelgeuse can even dim to the point where it's only about 35% of its original brightness. So these unusual pulsation events can be extremely hard to predict. Now, our Sun also has a little bit of variability, but it's not as dramatic as some of these other stars. The solar cycle lasts for about 11 years, and it's a lot less dramatic than some of these other star systems, which is actually lucky for us, because for us to have actual stable conditions for life on the planet, we do need to have a stable star. So many scientists believe that this might be actually one of the reasons why life was able to form in the solar system and might not really exist in other star systems. Although this is just one of many reasons why we think solar system is just one of those lucky systems. But when it comes to binary stars, the scientists have always speculated that there could be a system where the pulsating is actually sort of driven and controlled by the partner star. In other words, because these two stars would orbit relatively close to one another, and because of various tidal effects, the pulsations could be completely driven by the star orbiting the larger star. So essentially, several decades ago, scientists predicted that there could be a system where the pulsations only happen on a single side of the star, while the other side, the opposite side, stays completely undisturbed. And for the first time ever, we've found such a star. This is what the scientists believe is probably happening there, and this is probably why it seems to be pulsating only on a single side. If you look really closely, you'll see how the star seems to actually stretch a little bit toward the smaller partner. This is all because of the tidal effects caused by the partner that orbits around the star. It takes approximately 1.6 days per orbit, and on the side where the smaller star is located, that's exactly where these pulsations happen. And the larger star, known as HD 74423, is approximately 1.7 times the mass of our Sun, so it's a lot more massive, it's also larger in size, and this system is located approximately 1500 light years away from us. But the smaller partner here is just a typical red dwarf. And despite this system already being so strange, there are other unusual phenomena here as well. Specifically for scientists, they can't really explain why the system is so low in metallicity. And what metallicity implies is that these stars are made of predominantly hydrogen and also helium, but possess almost nothing else. In other words, there are very few non-hydrogen and non-helium elements, which usually suggests that these stars are really old, from one of the earlier generations, and also that they probably don't possess any silicate planets. At the same time, the scientists are not entirely sure if the pulsating actually happens on the side facing the partner, or if it's on the opposite side, because right now there's no way to actually try to find out which direction these pulsations came from. So in other words, it could technically be on the opposite side, despite this simulation showing it as the side facing the partner. At the same time, we're obviously not entirely sure how the system formed, how the pulsations originated, and most importantly, what's going to become of the system later on. Basically, are these stars going to collide with one another? Is one star going to escape somewhere else? Or is this a more or less permanent system? Although at the moment it does seem like at some point the partner star might actually collide with the larger star, which could of course trigger some sort of a large catastrophic event, like what you see right here on the screen. And what's really important about this study and a lot of other astronomical studies is that, just like with previous unusual discoveries, this too was actually discovered by citizen scientists, and only then was brought to attention to scientists working for universities. In other words, this is just another example of how amateur astronomy has advanced so much, where a lot of really cool discoveries are actually made by people like you and me. And since this discovery was made using the beautiful NASA's TESS telescope, that's essentially meant to replace Kepler's discoveries and find a lot more exoplanets near us, you too could join this community and become a citizen scientist by joining, for example, this right here. I'm posting the link for this in the description, but essentially this is a combination of very small mini-games that are used to help scientists classify various detections made by the beautiful TESS telescope that can then be used by actual scientists to study this in a little bit more detail. I've done this a few times myself, it's kind of fun, it's a good sort of time waster, and it obviously helps scientists and science to advance a little bit faster. But most importantly, because TESS data is actually completely free and available to everyone, one day we'll also talk about how you could try to find a planet yourself by using all of the data that you can download on the internet. Although it's probably going to be a slightly longer and a little bit more complicated video. But anyway, until we discover more and until we find more unusual stars and planets, that's really all I wanted to talk about. In some of the future videos, especially when James Webb Telescope becomes operational, I'm sure we'll actually talk about something even stranger. Hello wonderful person, this is Anton, and in this video we're going to try to talk a little bit more about what may have existed before our universe, if anything. We're going to discuss this new study that came out very recently that may actually present at least one answer of what existed before our own universe, before the universe expanded, and obviously before the Big Bang itself. But before we start though, I really have to say that right now, as of today, we kind of have no idea if anything did exist before the Big Bang, and if anything was out there before the universe came to be. As of today, as of 2020, our understanding of the timeline of the universe kind of stops somewhere right here, basically a few fractions of a second after the initial creation of the universe. Now, even at this point, there are still some speculations that things may have gone differently, but for the most part, we kind of don't really know if anything at all existed here. However, at least one scientist, this wonderful person, Roger Penrose, has been arguing about the idea that the universe itself has been created and destroyed several times over the eons of existence. This concept usually goes by this name, although sometimes it's known by different names as well, and generally we refer to it as cycles of time. And even though you may have never heard of Penrose before, he's actually on par with Stephen Hawking in terms of various ideas and theories he proposed over the years. He's one of the most distinguished modern theoretical physicists and has won a lot of different awards. But anyway, that's not really the important part. Today we're really trying to figure out what exactly is he proposing and does it have any merit. So in his theories, what he suggests is that if we were to try to go back in time and essentially reach the point where the Big Bang started happening, which is of course this point right here somewhere, there might be signs for us, or there might be actual evidence there that suggests that something else may have existed. And for many years, he suggested that we can actually see these signs in the so-called cosmic microwave background. Now, you might remember what cosmic microwave background is. This is the so-called CMB. And essentially, this is the first light we get to see from the beginning of the universe, when approximately 375,000 years ago, the universe itself cooled down enough for various protons and electrons to start combining, creating a lot of neutral atoms, and thus allowing the light to actually move around the universe. It was no longer opaque, it was no longer absorbing light. So some of this first light is what we see in the CMB. And over the past few decades, our ability to see the CMB has improved quite dramatically. This is from back in 2003, and this is the most recent one from 2013. So the accuracy of us seeing this light, this first light in the universe, is improved enough for us to actually see specific details in it. And according to Penrose, in this CMB, in these lights, you can actually find clues suggesting what happened before the Big Bang. And for a very long time, he was absolutely adamant, he was pretty certain that we could actually see the remains of the past universe in this CMB. In other words, we could possibly see the signs of the previous universe or whatever else existed before our own universe. And so it's really interesting that he's been pursuing this for many years now, and a few weeks ago his team released another paper suggesting that there's actually quite a definitive sign in the CMB that suggests something may have happened before our universe. And that something was very likely extremely massive, extremely large black holes that disappeared over time. So here's what they actually proposed they found in these observations from the cosmic microwave background. By looking at the older data and combining it with the newer data, they were able to identify several pieces of evidence suggesting that there were these unusual and relatively large rings that were apparent in some of the data that could only be explained as some kind of artifact from whatever happened prior to the existence of our own universe. And some of these rings and some of these unusual formations in the CMB are usually explained with the early turbulence in the existence of the universe, but some of them are difficult to explain without introducing some other ideas. And in this case, they believe that some of these very specific formations can only be explained by something else that happened in the past. Basically something that influenced our own universe even before the universe began itself. And they're proposing the following. They're basically saying that these extremely massive black holes that existed at the end of the last universe started to emit a lot of Hawking radiation, which we know very likely is being emitted by all kinds of black holes in our own universe right now as well. And due to the sheer size and mass of these black holes, the effects were so large that they now are visible in our own universe through these unusual rings and other deformations in the CMB. Which kind of implies that the last universe very likely ended with the existence of these really massive black holes during the so-called last black hole age of the universe. Today we believe that maybe at the end of our universe we'll have something similar where nothing but black holes are left, and eventually even these giants will evaporate, leaving nothing behind. So in some sense, the evidence from the CMB does seem to suggest, at least according to Penrose, that this is exactly what happened with the last universe before the Big Bang caused our universe to begin as well. So in other words, what he's suggesting is that all of these ancient black holes from the previous universe, as they evaporated one by one, left little marks that are now seen in the CMB of our own universe. And this is something that's kind of really difficult to wrap your head around, but he does explain it using a lot of theoretical physics and a lot of modern theories that do kind of suggest that maybe he's right. However, there is a small problem with all of this, and the problem is that according to his theories, all of the universes will then end the same. They will all end up with the so-called Big Crunch, where essentially the entire universe slowly condenses into a tiny point yet again until the restart of the new cycle. But the problem here, of course, is with the evidence we have from the last year or so. There was a study that seems to actually discredit this, suggesting that the universe will most likely end up ripping itself apart, the event we refer to as the Big Rip. The evidence for this was quite substantial, and I've talked about this last year, so in that sense there's a bit of a contradiction. Unless, of course, our universe is completely different from the previous universe. Maybe what's happening now is something unique and something that hasn't happened before. But at the moment, there is nothing to say that he's actually wrong, and there is a lot of evidence to suggest that he is right. Unless someone can explain some of these observations in the CMB using some other idea or some other theory. For now, there's no better explanation. And although still theoretical, this proposal can of course explain a lot of other things. There's actually a lot of really interesting other theories that he proposes, including the so-called information panspermia, which basically implies that technically by using the communication between the previous universe and this universe, some super advanced extraterrestrial intelligence could have actually found a way to transfer all of the information about life to our universe to begin it here as well. And all of this cosmological information could have actually been also stored in the CMB, eventually making its way to various planets across the universe. Now this is a really far-fetched idea, there's really currently no proof of any of this, but it's still an interesting idea to explore, especially as we learn more and more about the CMB itself. There are still quite a lot of mysteries about this unusual background radiation. But unfortunately, all of this is still very theoretical. It's going to be extremely difficult to prove any of this, and we'll need a lot more, much more powerful observations of both the CMB and the universe around us to try to see if any of this makes any sense. At the same time, trying to disprove this is also quite difficult because, once again, we don't have enough data or any alternative theories to try to suggest that these ideas are incorrect. So for now, it's something to think about, something to ponder, and I guess in some sense, it's good to know that at least one scientific study was able to prove the existence of so-called cyclical universes across the ages. In other words, the universe being created and destroyed. We obviously don't know how many times, or if the other universe was different in any way in terms of the actual physics. But all we know for now is that there are definitely going to be a lot of follow-up studies to try to talk a little bit more about this, especially from the theoretical physics perspective. Hello wonderful person, this is Anton, and in this video we're going to be once again talking about the now famous Betelgeuse, and some of the more recent discoveries and some of the more recent news about this unusual but somewhat familiar star. So in the last few weeks I've been getting a lot of messages about the status of Betelgeuse. More specifically, a lot of people really want to know, so what's really happening here? Is it exploding? Is it just dimming again? Or is something else peculiar happening here? And the answer is, well, the latter answer. Something really weird is going on with this unusual star that we're going to be zooming into right now. So Betelgeuse, as you probably know by now, is a star that's roughly around 650 to maybe 700 light years away from us. And it's a very famous star. It used to be one of the brightest stars until, I guess, very recently. And let me show you what has changed in the last 2 months or so. Here's what the visual data for Betelgeuse looks like. This is approximately 2 years ago, this is approximately 1 year ago, and this is basically now. And you can see how it suddenly dips right here. It drops to the point where it has now become about 35 to 36% of its original brightness, decreasing by about 65%, which is a huge value. And as of today, we still have no real answer on what's really happening here, but we know that it's not really going supernova. That's like 99.9% certain. And one of the reasons we know so is because of the recent picture that was taken by the incredible European Space Observatory, whose video you can see right here. So what exactly did they discover? Well, in the video that was recently posted by ESO, they showed us what could possibly be responsible for this dimming. You'll see it in a few seconds, and I'll show you the before and after picture as well. So here, this is what Betelgeuse looks like right now. This is literally the most recent photo we have of this object, and you'll notice that there is something unusual right here on the bottom. Now here's what the before and after picture looks like. This is in January of last year, and this is now. Notice how something did happen to Betelgeuse, and it does kind of explain to some extent what's probably happening to this star. And one of the best explanations that was given so far is that because it's such an expanded, such a giant object, and because it actually doesn't really act like a typical star like our sun, for example. For example, it's not such a compact object as our sun, and is more like a kind of a plasma cloud that surrounds a really large area. So in that sense, it behaves completely different from what we expect a typical, more compact star to behave. And this is of course because this is the last stage of a typical main sequence star, when a star, even a star like our sun, expands dramatically, covering a tremendously large area, which essentially means that it would cover most of the solar system if we were to place it in our solar system. But once again, this simulation here does not really accurately represent what these supergiant objects look like. They're very likely a lot more like a cloud than they are like a star. And because these giant stars act so differently and also actually expel a huge amount of mass all the time, we think that there might have been a very large ejection of mass at some point, and as this mass moved away from the star, it essentially covered the star itself. So in other words, it's probably some sort of a large dust cloud that's covering Betelgeuse, decreasing its luminosity so dramatically. At the same time, it also seems to have changed its shape a little bit, and we can't really explain that yet, but it's unlikely to do anything with an impending supernova or any other cataclysmic event that would destroy the star. And the other explanation, the second explanation, relates to the idea of maybe this star also, because of some sort of an event that released a lot of dust, cooled down a little bit and decreased in size. In other words, because of the way that the star evolves with time, and it's going to be doing a lot of this for the next 100,000 years or so, it might have shrunk a little bit simply because of the way that the star always oscillates and always changes its shape and its brightness. This is, after all, a variable star, which you can easily see in this light graph, because you'll notice that even when it's acting normal, it still changes its brightness a little bit, and it's not really that predictable. So this is because this is a very unusual variable star that does have a lot of various cycles going on inside. And also, just to help you visualize this yourself or help you track this yourself, I'm posting this website in the description below. And this is an association of astronomers that observe various variable stars and post data online for everyone to see and for everyone to use. This light curve generator is really easy to use. Basically, all you have to do is enter the name of the star and then enter the number of days you would like to observe it for. You can also change some of the parameters here to see different, for example, different frequencies of light, but I usually just do this just to see the visual light. And once you plot your data, you'll start seeing both the graph itself and also all of the people responsible for taking some of these measurements. But in some of the recent observations, you'll notice that it started increasing in brightness just a little bit. You can even see more of this if you follow this account known as Betelgeuse Status, created by this wonderful person, Michael Hipke of Germany, who's actually an independent astronomer. And he's been posting a lot of various updates on what's happening to Betelgeuse, and here you can kind of see that it's slowing down, it's dimming, and more recently you'll notice that it even started increasing in brightness, just a little bit. In other words, once again, it seems that whatever Betelgeuse was doing, it stopped doing that and is now sort of reversing its course. So once again, this confirms the idea that it was probably something related to dust or maybe some kind of a major shrinking of the star due to some of the cycles inside. And this is further reinforced by some of the other observations in infrared light by the so-called visor. When comparing the surrounding environment of Betelgeuse with the picture that was taken in 2011, the more recent picture from December of 2019 shows a huge amount of dust around Betelgeuse that is very likely responsible for all of the dimming we're observing. In other words, in the last 9 years, a lot more dust has accumulated around Betelgeuse, and it's probably just blocking a lot of the light. And because we think Betelgeuse, or typical stars that are like Betelgeuse, these supergiant stars, are normally filled with these really large convective cells that you see on the surface here, that also move and shrink and change size all the time, at the same time affecting the star itself, that allows the star to also change its size dramatically. All of this together helps us understand that these objects are very dynamic, they're very active, and they have a lot of different activity on their surface and also inside of them. Which is why, once again, it's somewhat difficult to imagine what they really look like, but they're very likely nothing like our own sun. And although I guess that's not as exciting as hearing about an impending supernova, there's still a bit of a mystery about those gravitational waves we've detected here. The video about this is somewhere above my head, but basically we did detect gravitational waves coming from the vicinity, or at least the Orion neighborhood, very close to where Betelgeuse is located. There's still not really a good explanation to what caused those unusual gravitational waves, but hopefully in the next few months we'll be able to answer this question as well. It's not probably going to explode, it's also very likely going to start brightening again very soon, but at the same time you can follow its progress both on Twitter or by looking at the website that I showed you here that has all of the up-to-date data. On that note, if by some unusual accident Betelgeuse does explode, well, in that case, I'm going to make sure to follow this up with another video explaining how I guess I was wrong and things didn't go as planned. Hello wonderful person, this is Anton, and in this video we're going to be continuing talking about the famous star known as Betelgeuse that you can see right there in the night skies of our planet. A few more interesting facts just came out about this star, and one of them involves gravitational waves. The incredibly large, beautiful and bright Betelgeuse that you see right there in the middle is technically known as the Arm of Orion in different languages, and Betelgeuse itself stands for the Arm of Orion in Arabic. This star is so extremely large and expanded so much over the years that it can easily be seen with a telescope, and with a powerful enough telescope you'll even be able to see something like this. The actual features will become visible. As mentioned in some of the previous videos, if you were to place this star in the middle of our own solar system, it would sort of look something like this, covering pretty much most of the terrestrial planets and reaching almost all the way to the orbit of Jupiter with a radius that's about 900 times the radius of our own Sun. So this is a tremendously large, very bright and very powerful star. But the thing is, on January 14 of 2020, something very unusual has been reported by some of the scientists working for LIGO, which is of course this large L-shaped detector that was responsible for detecting gravitational waves when various black holes and neutron stars collided, allowing us to study effects we've never been able to study before. You can actually even see this report yourself on the so-called GRACE database that keeps track of all of the gravitational waves and has a really accurate, up-to-date approach to posting all of the gravitational waves pretty much as soon as they're detected. So here, on January 14 of 2020, these scientists reported detecting unusual gravitational waves coming from the same region where the Orion constellation is located. And because this was only a few weeks after we detected the dimming effects, this obviously raised a lot of interesting questions. Is Betelgeuse actually going supernova? Did it finally explode, and are we observing some unusual effects, including the gravitational waves that we think some supernova might produce? And according to the LIGO researchers, this is the unusual burst wave gravitational wave that we don't really have a good explanation for. So technically it could have been an actual explosion or a supernova. But at this point, we're not even sure if this is a real detection or if it's something related to a disturbance here around Earth that might have created this as well, because LIGO is so sensitive that it can technically detect things that are created by all sorts of mechanical and electrical things on the planet. In other words, for now this report is very preliminary, but a lot of scientists studying Betelgeuse were super excited, and some of them even went outside to check if it's still there, because maybe it has gone supernova. And as of today, at least the last time I checked, it's still there. It still hasn't exploded. And one of the astronomers, Andy Howell, has even gone as far as making a small map showing us where Betelgeuse is and where these two detections are in relation to Betelgeuse. In other words, he kind of demonstrated that they weren't really exactly where the Betelgeuse is. They could have come from any other region here and here. But just the fact that we've detected a gravitational wave so soon after we start reporting the dimming effects of Betelgeuse is exceptionally unusual, and I guess in some sense a very crazy coincidence. But today I think most scientists would agree that it still has probably a few thousand, possibly even 100,000 years in it before it actually does go supernova. Currently Betelgeuse has existed in this form as a giant for roughly around 80,000 years, but it still has way more to go. But furthermore, one of the new models that was recently posted, because Betelgeuse suddenly became a very famous star to talk about again, suggested something else really interesting. It suggested that possibly Betelgeuse has even more than originally thought. In other words, it might not be going supernova anytime soon at all, for a very simple reason. Over the last few years, the scientists studying Betelgeuse discovered that there are two unusual properties that it has. One of them is that it seems to possess a tremendous amount of nitrogen that shouldn't really be here. And the other is that it seems to be spinning way faster than it should be spinning. Because it's such a tremendously large star, as stars expand, they should be slowing down their rotation. They should not be spinning very fast. Betelgeuse, however, spins pretty fast. Possibly as fast as 15 kilometers per second on the surface here. And this presents another unusual problem that we can't explain. But one of the recent studies tried to tackle that. And by using various models, the scientists have been able to explain these unusual properties along with the origin of Betelgeuse relatively accurately. So first of all, we know today that it was very likely created in this very dense star region known as Orion OB1A, and it very likely also got kicked out of here and moved all the way to where it is today. We know this because Betelgeuse is actually moving relatively fast across the night skies, and it's leaving this particular system. But hypothetically, if Betelgeuse was not one star, but a binary system, with two stars orbiting around one another in this fashion here, and one star being about 16 masses of the Sun, the other one being about 4 masses of the Sun, once they got kicked out of this original home system, their orbits would actually destabilize a little bit, and with time these two stars would slowly start approaching each other and eventually combine into one. In other words, these stars would turn from binary system to a singular large object that would then start mixing its material and also create a lot of spin momentum, which would explain why the modern Betelgeuse is spinning so fast, and also by combining the smaller star with the larger star, some of the nitrogen that was already created here would have actually stirred up, bringing it to the surface, which is why we're seeing so much of it today. In other words, if the Betelgeuse star was a binary system and was then merged into a singular object, it would actually have all of these features that we're observing today. But on top of this, if this is what happened, it's very likely that it still has so much material in it that it shouldn't really be going supernova anytime soon. As a matter of fact, this new discovery or this new analysis suggests that we might have overestimated when Betelgeuse is going to go supernova. The scientists behind this paper now think that it actually is not going supernova for a very long time. And this particular idea makes a lot of sense. As a matter of fact, we already know today that some of the unusual peculiar observations we have of stars can usually be explained if the star itself used to be a binary system. Like for example, very recently I've talked about the G objects, and today we know that these unusual G objects that otherwise are very difficult to explain can be very easily explained if two stars are merged to create the object that we're observing. So in a sense, the binary system becoming a singular star can explain many different phenomena we're observing today. And this could of course apply to Betelgeuse as well. But we need a lot of follow-up studies for this to become a fact. For now, it's just an assumption. Although a very sound, very scientifically accurate assumption. Assumption that I personally really want to be true. But we'll find out with time if this is correct. And the thing is, if this was a binary system that became a singular star, this could be our best opportunity to study the evolution of such unusual systems. In other words, by studying what's happening with Betelgeuse and trying to understand what effects this has on the actual star system, we might be able to then create a lot of other ideas and a lot of other theories to help us explain other mysteries in the universe, specifically related to, like for example, dimming stars like the Tabby star, or other unusual phenomena that are currently unexplainable to us. But anyway, that's kind of it for the updates of Betelgeuse. So first of all, we've detected gravitational waves, and secondly, we also think that maybe, just maybe, this used to be two stars, in which case it still has a lot of fuel left before it becomes a supernova. Hello wonderful person, this is Anton, and in this video we're going to be talking about the biggest explosion in the universe. Once again, because we just found something that was even more powerful. So it seems that once again we've discovered something that beat the previous record, and specifically here we're talking about the biggest explosion we've ever detected, or at least the signs of that explosion that very likely happened a few 100 million years ago. But before some of you say, but wait Anton, if that's even your real name, isn't Big Bang the biggest explosion in the universe? Instead of explaining it myself, I'm going to point you toward the videos of amazing Dr. Don Lincoln, who explains a lot of the Big Bang misconceptions really well. He's one of the major scientists in Fermilab, and he explains these concepts really well. So check out some of his videos to kind of learn more about why Big Bang is actually not an explosion at all, but more of an expansion event that's still going on. Yet there was a video that I made about 2 months ago that was actually called Discovery of the Biggest Explosion in the Universe, that was about, back then, the biggest explosion we discovered. But what the scientists discovered just now very recently beats this record by about 5 times. So the explosion event that happened in this region known as Ophiuchus is about 5 times as powerful as the previous record holder. Now this is why it's kind of exciting, because we never imagined such events to even occur. In a nutshell, all of this happened not so far away from us in a galactic cluster known as Ophiuchus. If we look at the map of the universe of nearby galactic clusters, this is roughly what all of this looks like. Our galaxy is inside the Virgo supercluster and is being pointed at by this arrow right here. It's really tiny in this image. And if you were to go this way for about 390 million light years, you'll discover the cluster known as the Ophiuchus. And if you were to start zooming in on this, eventually you would discover this area here that's roughly a few million light years across. And this is exactly where the scientists just discovered what seems to be the signs of an extremely large explosion from the center going this way. And the reason they know that this is an explosion, or it was an explosion a few 100 million years ago, is because of the actual structures and the emissions happening here. There are a lot of X-rays coming out, and there are also a lot of radio emissions, all together forming in the same region in the same shape. As if something in the center suddenly exploded, releasing all of this energy, in a sense resembling a kind of a volcanic eruption on Earth, but here this is on galactic proportions. And the volcano itself is in the middle, and suddenly all of this energy came out of here and created this cavity that we see on the screen. And all of this was determined using various frequencies and a very thorough analysis that essentially presents us with a kind of a picture where something in the middle caused a tremendous release of energy that then created this edge that is otherwise almost impossible to explain. Whatever this emission was, it was so powerful that right here there's actually a kind of a hole in plasma that's otherwise present around the galaxy, and this super hot gas created an actual discontinuity right here, and it's visible in every spectrum. In terms of the actual size of this, I guess you could call it crater or a galactic crater, it's about 15 Milky Ways across, or essentially several million light years across, which makes this a tremendously large and very unusual formation. But obviously we've seen many other outbursts and explosions in other galaxies, but normally they're not really even close to being as powerful. What we saw here is equivalent to roughly around 50 billion supernova. Now it's obviously very difficult to imagine such a huge number, but if this is just one supernova, and this here is about 10 supernova, now multiply this by a billion. Anyway, it's really difficult to imagine such a huge amount of energy being released, but this energy, as it was released, essentially created this unusual formation. And obviously we don't really know why, how, or what created this, or how this was even possible. We obviously suspect the supermassive black hole in the middle, but the amount of mass that this black hole had to actually consume suddenly is kind of difficult to explain. Although actually the scientists don't think that this happened suddenly, they believe that this was probably over a period of several million years. So it's quite possible that something really massive, like for example some sort of a massive gas cloud, was absorbed over a long period by a supermassive black hole and created this really large emission. And one of the reasons we've only discovered it now, even though it's so close to us, is because we never really bothered to look at this particular galactic cluster in radio waves. We always either looked at it in X-rays or in visual light. But now the scientists decided to take a look at it using radio waves as well, and this is when they saw this unusual formation that was present both in radio waves and also in X-ray radiation as well. And both emissions were more or less aligned with each other, forming this unusual crater-like shape. Now right now we obviously have no explanation for much of this. This is only just an interesting discovery. There's really no actual ways to explain what exactly causes such events, or if such an event can happen in our own galaxy, or if this even had any influence on our galaxy. But nevertheless, this is still interesting to us because currently this galaxy is extremely quiet. It's a very quiet radio galaxy that still has an active galactic nuclei, but in comparison to some of the other galaxies and even in comparison to its own past, it's extremely low in luminosity and it doesn't produce as much radiation anymore. And so the scientists now think that because of this huge explosion, whatever happened back then, this galaxy kind of sort of made itself extremely quiet. It sort of expelled a lot of material that was around it, creating something that's a lot more quiet now than it used to be before. And this is what they believe may have happened approximately a few 100 million years ago. And if these large explosions can change galaxies so dramatically, this actually means that some galaxies could be completely destroyed by these large explosions. And if these large explosions can actually quiet galaxies, what if they can also destroy them? What if an emission can be so powerful that it can totally blow the entire galaxy apart? Now this is something we've never seen before, but we obviously haven't really looked that hard yet. I'm sure it will take a few years, but we'll probably discover even more signs of even bigger explosions out there. And interestingly, when the scientists originally found this, they actually kind of didn't even believe that this would be a powerful explosion because it was just way too powerful to exist. It took a lot of follow-ups and a lot of additional observations to finally admit that what they were looking at was what seems to be the most powerful explosion we've ever seen anywhere. And it doesn't seem to be that far away from us either. It's a lot closer than any of the previous findings. Now, if something like this ever happened in the Milky Way galaxy, chances are a lot of gas and a lot of stars would just completely disappear or at least get kicked out of the system. And since we see that such explosions are even possible in the universe, it also kind of slowly takes us closer and closer to answering the questions about why we're not seeing any extraterrestrial intelligence out there. Our universe seems to be a lot more violent and a lot more unpredictable than anyone ever imagined. If such an explosion occurs near our galaxy, I'm pretty sure that most of the life on our planet would perish really quickly. And so maybe the answer to Fermi paradox is that we are really, truly the only survivors in this madness of the universe. Hello wonderful person, this is Anton, and in this video we're going to be talking about one of the more mysterious topics in the universe, the cosmic web. And more specifically, I wanted to try to answer the question of how bright it really is based on one of the more recent papers that I just discovered. Now, a cosmic web is also sometimes known as the galactic filament, and it's essentially these sort of invisible or very, very difficult to see strings across the universe that connect pretty much every single object, including our own galaxy. Normally, when we look at galaxies or when we try to imagine galaxies, this is sort of what we see, at least that's what a lot of media presents this as. And also, I guess, when you look at the night skies, this is kind of what you'll see as well. And that's mostly because the galactic filament or the cosmic web is very, very difficult to see. As a matter of fact, a few months ago I've talked about the first ever picture that we were able to take of it, and this was using extremely sensitive instruments. So it is there, but it's just difficult to see and almost impossible for us to actually measure using normal means. So we have to kind of improvise and use a lot of really interesting techniques to try to figure out what's going on inside of this web. Now, its existence has been predicted for a very long time, and we know that it's there from various different sources. And for the most part, what's inside of this web is, of course, the mysterious dark matter. Cosmic web itself is also kind of the telltale sign that dark matter does seem to exist, because there are these unusual features that are present in this region of space that is not actually visible. So I'm using this beautiful simulation known as the Illustris project that tries to simulate the universe using all of the modern features. And here, this is what the star map looks like. Then if I were to switch this back to the dark matter map, this is exactly the same space, but now you can actually start seeing an actual filament, because for the most part it's made of this mysterious dark matter. But at the same time, there's also a lot of gas here that also connects along the filament as well. So if we were to combine these two together, this is kind of what it would look like. So here you can kind of start seeing both dark matter and gas interconnecting. And today we believe that the vast majority of mass in the universe, and that includes all of the visible mass, is actually in the galactic filament in the so-called intergalactic space. I've talked about intergalactic space in one of the previous videos, it's going to pop out somewhere near the end of this video, but essentially, in a nutshell, a lot of different mass is sort of missing from our observations of the universe, and we think this mass is actually hiding in the galactic filament. And there is so much gas here and so much different mass that we think it will never even become anything, it will just stay gas for the rest of the existence of the universe. But not everything here is gas. There are still occasional stars and even globular clusters present here, and we've even seen signs of actual star formation as well. So in that sense, it does produce some light, just not a lot of light. And the light that it does produce is very, very difficult to see because it's just really, really stretched out across millions of light years. But based on this picture and all of the studies we've done so far, we know that all of the galaxies are connected with this, and actually some of the recent discoveries even suggested that the vast majority of galaxies are specifically aligned along the filament. This was discovered by looking at different quasars, and we discovered that they all seem to be pointing in more or less the same direction as they move across the filament. So in some sense, this suggests that these unusual cosmic strings are sort of controlling the whole universe. But trying to discover its brightness is a really difficult task, and so the scientists, whose paper you can find in the description below, used a very interesting technique to try to once and for all discover how bright the filament actually was, in order to actually get a mathematical model so we can use these numbers to then look for it in other parts of the universe. But to try to even find this filament, they had to use some really extreme examples. Here they used galaxies known as LRG, or luminous red galaxies. Now, these galaxies are typically extremely bright, but they also are more or less red in color, like the one you see right here. This is because they mostly contain really ancient stars, very sort of reddish stars, and a lot of gas. This galaxy is actually very familiar to all of you. This is the M87, whose black hole picture we took only a year ago. The most famous LRG is actually IC1101, which is also the largest galaxy we've ever discovered. I made a video about this a few years ago, but essentially this is as big as it gets. This is basically a galaxy that's a few million light years across. But they didn't really use these galaxies. They wanted to find galaxies that came as pairs. So they were specifically looking for LRGs that came as a kind of a binary in order to then see what's happening between them. And so here they combine various different pairs and then remove the galaxies themselves, leaving behind only what appeared to be the connection between them, or the so-called cosmic strings, also known as the galactic filament. Now there are probably other ways we could have seen this filament, like for example here by taking a picture of a much larger area, but this would not really allow us to very easily calculate its total brightness. By using the actual galaxies where it's located, we can then extract the brightness of the galaxy and calculate just the difference of this brightness here. And so by doing this with practically several dozen pairs of different galaxies, they came up with an average value of 351 plus minus 87. Now what this means is that for every 351 masses of the Sun, there's about one luminosity of the Sun. So let me help you imagine this. Right here I placed about 350 different stellar objects, Sun-like objects, all of which you can see if I select them. But the thing is, the only visible object is this really tiny spot in the middle that you might be able to see. It's extremely difficult to see, but this is equivalent of about 350 masses of the Sun with only one single luminosity of the Sun. If I were to zoom into this object, you would discover that, well, yes, this is indeed a Sun-like object. But because overall it's kind of hidden by all of the other mass, it's almost impossible to see it from a distance. And the farther you go, the more invisible it becomes. And so in a nutshell, they discovered that the average luminosity of cosmic web was about 1/351. In their paper, they refer to this as the mass to light ratio. But this could also be only for some of the brighter parts of the so-called cosmic web. There could be other parts that are a lot less bright and also could be almost impossible to see, which is why their error value is approximately 20% or so. But overall, this is a very interesting study and actually an important next step in trying to identify other techniques on how we can study cosmic web a little bit more. This is an extremely important part of our universe, and because it has so much control over all of the galaxies, this is actually why we need to know a little bit more about it and understand how all of this evolved our universe over the last 13 billion years. But since the universe is expanding and a lot of matter ends up either going into the galaxies or essentially these cosmic strings end up being even more stretched, over time this luminosity will actually decrease even more, and it's possible that in a few billion years it will be almost impossible to even know that the cosmic strings exist. It's also very possible that in a few billion years, if there is some sort of a super intelligent species, they might look at the night skies and actually not even realize that something like this was even there. They might not even know that this intergalactic connection ever existed. But they also might not know about other things. At some point, they might not even see other galaxies as well. Hello wonderful person, this is Anton, and in this video we're going to be talking about a very recent study that may have identified at least one really good candidate for what dark matter could actually be. In other words, scientists may have finally discovered at least one particle that could represent dark matter, assuming of course we discover it somewhere out there. So if we look around the universe, we'll discover a lot of signs pointing at the existence of the mysterious dark matter, but so far still no good explanation of what's really causing it. But there have been a lot of interesting discoveries in the last few years, and more specifically one discovery in regards to this unusual particle that was identified back in 2011. And it's basically a type of a particle that we refer to as hexaquark. Now, I'm gonna have to explain some things here. First of all, let's look at a typical atom. This here is helium, and what you'll see inside the typical atom are 2 protons, 2 neutrons, and here we have 2 electrons to make this a neutral atom of helium, which is basically the second most common element out there. Now the atom itself is a whole piece, you can actually move it around, and I've seen this done in a lab here in Seoul, where an atom of iron was actually moved with a little needle in order to create a certain pattern. So these tiny pieces create a larger piece. But then if you look inside of, for example, proton and neutron, you'll discover that they're also made of other stuff. And I remember asking some of my teachers in high school, what are they made of? And the answer I got was quarks. But that's where the teacher kind of stopped because, well, as they explained to me later, this was really complex and even beyond their understanding. And as I kind of started learning about this myself, I nodded and said, yeah, this stuff is really complicated. So as we go down into the subatomic scale, things do get a little bit more complicated. And by combining these different types of quarks, you also get different types of particles. So for example, if you combine 2 up quarks with 1 down quark, you get a proton. And by combining different types of quarks, you get different types of particles. And although a lot of them do have 3 quarks, it turns out that you can have more. As the scientists originally learned in 2011 and then confirmed in 2014, hexaquarks also exist. And they do seem to be extremely strange and very different from anything we've ever seen. They don't seem to exist here on Earth, this was created in a lab, and they only lasted for a tiny fraction of a second. But that was enough for scientists to start asking questions of what exactly is this particle, and could this be the dark matter that we're looking for? And so now, a few years later, the 2 scientists that wrote this paper decided to analyze this in a lot more detail and discovered that there's a huge chance that it can totally be dark matter. And according to these 2 scientists, the so-called hexaquark is capable of creating a very stable Bose-Einstein condensate. Okay, so another really complex concept. Bose-Einstein condensate, also known as BEC, is kind of in a sense another state of matter. So we're all familiar with at least 3 of them for sure, with the 4th one being also really important. So we have the liquid state, we have the solid state, the gas state, and the 4th state that's also very important is the so-called plasma state. We know all 4 exist on our planet and we can actually generate them pretty easily with things like increasing, decreasing temperature. But then there's the 5th state, which happens when things get really cold and when the gas gets really thin. And to try to explain to you what BEC is and why it's kind of important, here's a very short animation. So when a gas starts to cool down, eventually every atom starts behaving a little bit differently. As the atoms become colder and colder, their quantum nature becomes a lot more apparent. In other words, they start to behave a lot more like waves than particles. And as you cool them down even more, eventually they reach the state where their waves start to interact with one another and eventually actually combine into one large chunk. This chunk is what we refer to as BEC, Bose-Einstein condensate. So here you'll see it in a few seconds, and this becomes this huge kind of a quantum state where every single atom is connected to one another, and we can easily observe this and measure this. So this is a really important state, and it only happens at very low temperatures, very close to 0 Kelvin, and essentially it only happens when the gas is relatively low in density. But it just so happens that the analysis from these scientists determined that if you were to create conditions of extreme heat and extreme pressure, very similar to, I guess, the beginning of the universe, the hexaquark we discovered back in 2011 would actually form this BEC as well. They would create this really large Bose-Einstein condensate that would actually be relatively stable, would be able to survive for a very long time, and most importantly, there will be so much of it produced around the universe that it could easily explain all of the mysterious effects we're observing that seem to indicate the existence of dark matter. So in a nutshell, what these scientists suggest is that right here in the beginning of the universe, the conditions were just right for all of this BEC hexaquark stuff to be created. It then combined into these huge chunks of matter that most likely became stable over time and is still there orbiting around somewhere around the universe where we expect dark matter to be. And what's super important about this particular study and this discovery is that it doesn't actually invent any new physics. It doesn't seem to change anything about our gravity or about the way that the universe works. It actually uses the particle that we already discovered and confirmed. It uses the state of matter that we know really well, and it then uses it to explain the universe that we're observing. So here, everything seems to connect really well. The only thing that we're missing right now are actual physical observations of these hexaquarks somewhere out there beyond our planet Earth. Now, the scientists behind this paper already proposed several ways we could detect them. For example, they believe that by interacting with the upper atmosphere of our planet, they're going to produce a very specific cosmic ray that we can maybe find. Or we could use different space missions that are able to detect cosmic rays relatively accurately to try to find out if some of those cosmic rays came from the elimination of 2 hexaquarks that created a lot of energy. In other words, from the destruction of dark matter itself. And so even though technically right now it's still theoretical, the theory behind this is really good. Now, it might take a few years to actually confirm this or possibly disprove this, but I'm pretty sure a lot of scientists will become really interested in trying to figure out if hexaquark that we see right here might be responsible for the mysterious dark matter after all. And another way we could probably prove this is by creating all of this in the lab, by trying to create several of these hexaquarks and then seeing if they do behave in the way that we expect them to behave. But because they're kind of difficult to create, this might take a while. And honestly, no matter what we discover about hexaquarks, this is definitely one of the more exciting theoretical studies of the last few months. Hopefully within the next year we'll have a clearer answer on what's really happening with the hexaquarks and if it is really dark matter, but for now that's kind of all we know. Hello wonderful person, this is Anton, and in this video we're going to be talking about a new study that confirms a relatively old theory by Albert Einstein, the so-called frame dragging theory. But I think I have to explain it to you first. So what exactly is so-called frame dragging? The idea of frame dragging comes from Einstein's general theory of relativity. More officially, it's known as the Lense-Thirring precession, named after the two scientists who actually developed this idea back in 1918. And although it's kinda hard to imagine it, it's also not really difficult to understand. Essentially, when a massive body spins around, it will drag the space-time around it with itself. And to try to understand the effect, here's a very simple visual simulation. This object in the middle is massive and it spins. And as it spins, it actually drags with itself all of the actual space-time around it. And this creates this frame dragging effect that you can observe in this simulation. One of the more exotic examples from some of the recent movies is actually in Interstellar, where the effects of frame dragging of the ultramassive black hole called Gargantua create so much space-time stretching that one of the planets starts experiencing really dramatic time dilation effects. And this was the object known as the Miller's planet. If you've seen the movie, you kind of probably know what I'm talking about. But these effects don't just occur around very massive black holes. They also obviously occur around Earth because Earth spins. But because Earth is way less massive than a typical black hole and it doesn't spin near the speed of light, the effects are really minuscule. We didn't really know if they were real until back in 2004-2005, we launched a satellite known as Gravity Probe B, inside of which there was a very interesting device, a type of a multidimensional gyroscope that, as it moved around the planet and as the actual frame dragging occurred, was able to very precisely measure how much frame dragging our planet was producing. And as you can probably imagine, the numbers were extremely minuscule, but this was the first official scientific proof that frame dragging is not just a theoretical concept, it's an actual physical concept that exists out there. But today we'll talk about another really extreme example that scientists were able to just discover, once again confirming Einstein's ideas and the ideas by Lense and Thirring, the two scientists who actually proposed the idea to begin with. And this new discovery comes from a system of very unique, very unusual objects, these so-called compact objects, basically a white dwarf and a neutron star. In a nutshell, this is what, if you were to simulate the system, it would look like. We have the pulsar or the neutron star right there, the object closest to us, and in the back you're seeing white dwarf. If you remember, neutron stars usually form when a relatively massive star goes supernova and leaves behind a kind of a remnant. In this case, this remnant is approximately 2.5 masses of the Sun, and it spins about 2.5 times per second. White dwarfs, on the other hand, are formed by slightly smaller in terms of mass stars, and our Sun, for example, will also become a white dwarf. But both of these stars are very dense. White dwarf is not as dense as the neutron star, simply because it has less mass in a much larger volume. In comparison, the neutron star here has more mass in a very small amount of space. So the size of this object, the white dwarf, is about, well, similar to our planet Earth actually. Here's what Earth looks like for comparison, and a typical pulsar is about 20 kilometers in diameter, so this is the size of a relatively large city. And the scientists behind this paper started to observe these two objects roughly around 20 years ago. In other words, they've collected about 20 years of very accurate data on how these objects orbit around one another. And obviously they've discovered something a little bit unusual. The pulsar that was orbiting around the white dwarf was actually doing this. It was tumbling, and way too much. It was kind of moving around in a very unusual, very unpredictable way. At least unpredictable until they figured out what was going on there. Because normally, when a typical pulsar spins, you're supposed to see something like this. Here are another two very famous pulsars, and this is without the Einstein's ideas in there. So notice how the actual light beam always seems to cross the same location in space, and this repeats pretty much indefinite. Now the thing is, these two pulsars are much farther away from each other, and so they don't experience the same frame dragging effect. But because pulsars are so accurate and so predictable, we've even been thinking about using them as a kind of an atomic clock, much more precise than an atomic clock. The way that they pulse is extremely precise. Now, what about this other system? Here, something was causing this pulsar to tumble and not be as predictable, but eventually they figured out that there was a pattern, and this pattern was actually related to the frame dragging effect. In other words, they realized that the white dwarf was causing the pulsar to actually tumble because it was dragging so much space around itself. Here's kind of what all of this looks like. Notice how, as the white dwarf spins, the space around itself causes the orbit of the neutron star or the pulsar to slightly shift once in a while. And this shift is very predictable and easily observable using the theories I previously mentioned. And now that they were able to explain what's causing this unusual tumbling of the pulsar, they had to explain how this white dwarf acquired this unusual, very fast spin. And so they started to look around for various ideas on what could have caused the white dwarf to spin so fast that it produced these observable effects. These effects were essentially about 100 million times stronger than the effects that the satellite observed around planet Earth. And this is quite significant. This is essentially a very distinctive proof of Einstein's theories, and of course, the most accurate proof that the lens theory ideas are also correct. And ironically, neither lens theory nor Einstein believed that we would ever prove this, because they never thought it'd be possible. But thanks to the advances in modern technology and this beautiful telescope that you see here, we were able to finally prove this once and for all. So what exactly do we think happened here? Well, first of all, these stars are compact stars, but they're also remnants. They used to be actual big stars similar to our Sun. The star that turned into a white dwarf was probably a little bit more massive than the Sun, probably about 2 to 3 masses of the Sun, whereas the star that became the neutron star was somewhat equivalent to, I guess, the star known as Deneb. Here the mass was probably about 12 to maybe 15 masses of the Sun. These two stars very likely orbited around one another, and the scientists behind this paper believe that the Sun-like object became a white dwarf first. So basically, this turned into a compact object, not so different from the very famous white dwarf known as Sirius B. So as it transformed into the white dwarf, the other larger star also started to expand and losing its outer shell. And as it became bigger and bigger, some of its mass started to fall into the white dwarf. And the thing is, we know that when the compact objects receive mass, like for example through the accretion disk, they often start spinning up. They actually increase their rotation. This is how we believe so many various pulsars became extremely fast spinning, the so-called microsecond pulsars, essentially allowing these pulsars to spin so fast that if you were to stand on their surface, you would be moving at about quarter of speed of light. But in this case, the spinning happened to the white dwarf, so the white dwarf was spinning really fast. And because this other star was still expanding, eventually it reached the point where its envelope was touching the white dwarf. And this of course resulted in the white dwarf suddenly being bombarded with a lot more mass, increasing its spin even more, but most importantly, it actually started losing orbital speed. And this of course means that it slowly starts moving closer and closer into the star itself. And it's very likely that at some point it actually entered the star, and we can't really simulate this very easily here, but I'm going to try. So now we're sort of inside the star, and as this white dwarf consumed more and more mass, it spun up even faster while moving closer and closer to the central region of the larger star. And at some point something very likely triggered the supernova, while at the same time leaving the remnant behind, with the white dwarf and the pulsar being the only leftovers. And this is when the white dwarf was already spinning really fast and the pulsar was orbiting very close to the white dwarf, creating the system that we just observed for the past 20 years. But the thing is, it's not a particularly satisfying explanation, and one of the biggest problems that I'm having with this is, why is it that the white dwarf happened before the pulsar? Normally, neutron stars or pulsars come from much larger, more massive stars, which often live way less than typical stars like our Sun that turn into white dwarfs. Technically, the pulsar should have appeared first, not the other way around. So here there are still quite a lot of mysteries in the system that we need to resolve. There's a possibility that maybe this is actually a captured object from another star system, and this is something we'll need to discover in some of the future studies. And at the same time, we're still not sure what made the pulsar spin relatively fast as well. Something must have given mass as well in order for both objects to be spun up so much. In terms of the rotation speed, as I mentioned previously, the pulsar here spins once every 2.5 seconds, whereas the white dwarf takes approximately 200 seconds to spin once. But since this size is so different for both of these objects, the white dwarf definitely received a lot more mass to be spun up so much. But for now, unfortunately, that's all we know about this system, and hopefully some of the future studies will once and for all resolve the origin of this unusual system and how it came to be. But the most important discovery here is of course the confirmation of Einstein's ideas once again, and the most definitive proof of the so-called frame dragon effect that one day we'll be able to figure out how to use for practical purposes. But remember, 100 years ago, Einstein didn't even believe we'll ever discover this physically, and we just have. So imagine what's going to happen 100 years from now. We can only imagine what one day we'll be able to use this for. Hello wonderful person, this is Anton, and in this video we're going to be talking about the discovery of the fastest spinning star in our galaxy. So imagine for a second you were standing on the surface of our planet, specifically on the equator, where you would be moving at the fastest possible speed because of the rotation speed being the highest at the equator. Here, because of the rotation of our planet, you'll be moving at a speed of about 460 meters per second, or about 1600 kilometers per hour or 1000 miles per hour. So pretty fast, but not really as fast as some of the other objects in the solar system and also in the galaxy. Now, for example, if you were to stand on the surface of the Sun, in the same equatorial region, you would now be moving about 5 times as fast, approximately 2000 meters per second, or about 5000 miles per hour. So this is quite fast, but really not as fast as some of the other planets. The fastest spinning object in our solar system is Jupiter. And here at the equator you'll be moving about 6 times as fast, or about 12.6 kilometers per second. Now this is basically as fast as it gets in the solar system, and because of this really high velocity, Jupiter possesses quite a lot of various stormy activities on the surface, most of which do occur at the equator, and this is essentially where you can find the Great Red Spot of Jupiter as well. But even though the speed of rotation here is approximately 28 times as high as planet Earth, this is still not as high as some of the other stars out there. Now obviously we're not going to be talking about some of the more extreme examples like neutron stars, which can actually spin really fast, sometimes even pushing the boundaries and spinning at roughly around 30% of the speed of light. We really are talking about regular stars, stars like our Sun. And one of the best well-known examples of fast spinning stars is actually our neighbor Achernar. This is not really that far, it's only about 139 light years away from us in the constellation Eridanus. And this star is really bright, but it's also unusually shaped, as you can see. With the average mass about 7 times the mass of the Sun, it actually manages to spin once every 2 days. And the actual velocity here, if you were to stand on the equator again, would be approximately 250 kilometers per second, or roughly around 500 times the speed on the surface of our planet Earth. Now this has been actually a record holder for a very long time, but in the last few years we started discovering more of these unusual objects, and we found quite a lot of them having really similar properties as well. So for example, last year I talked about the fastest spinning star known as VFTS 102, but this is not located in the Milky Way, it's actually in a nearby galaxy of Large Magellanic Cloud in one of the more active regions of star formation near us, known as the Tarantula Nebula. Here there are a lot of really large massive stars, and some of them have really extreme records, and one of the records here is of course the fastest spinning star. But now we've discovered a very similar star, although this time with a much more complex name. And just like those other stars in the Large Magellanic Cloud, it seems to possess very similar properties. It's moving really fast across the night skies, it's spinning really fast, it seems to possess relatively similar characteristics in terms of the actual mass size and essentially all of the other properties, but most importantly, it's very likely not spherical. It's more likely a kind of a squished face with a really large disk around itself as well. Now this is really interesting because all of this is formed as a result of fast rotation. Mostly because as the stars start spinning faster and faster, the gravity at the equator starts decreasing due to the centrifugal forces. And we can even detect these gravitational changes by looking at differences between the polar region and the equatorial region. And because the gravity here decreases, the star starts forming this kind of a disk shape that eventually even starts throwing out some of the material from the equator, forming another flatter disk around it. More or less resembling something like this, but on a much larger scale. And all of this is a result of this star here spinning about 540 kilometers per second, or essentially around 1200 times faster than on the surface of planet Earth. All of this creates incredible centrifugal forces and a lot of other unusual effects that we're still trying to learn about, mostly because these stars are still relatively rare. Now, because of all of this material that's being thrown out at the equator, these stars actually produce a very different spectrum as well that we can easily detect. But unfortunately, as of a few months ago, we've only detected 13 such stars in our galaxy, now technically 14 with this new addition. So in other words, these stars seem to be pretty rare, and it's most likely to do with the way that they're generated and the way that they actually form to have this high velocity. Today we believe that the way all of these stars have formed is by actually having relatively large massive partners. And essentially, as these two stars orbit around one another relatively close, because of their mass and because of their generally large size, they kind of start breaking each other apart with various tidal forces, and a lot of the material here begins to slowly transfer from one star to another, and as this happens, one of the stars starts spinning up its actual rotation. All of this is actually due to the transfer of rotational momentum, but essentially with time, as the mass transfers more and more, the star starts spinning more and more. But eventually its partner becomes destabilized by all of this and initiates a supernova, which then ends up creating such a huge push on the star that it starts moving across the galaxy really fast. Which is why pretty much all of these stars we've discovered so far were so-called runaway stars. They were moving a lot faster than they should across the galaxy. But it seems like these conditions are extremely rare because we haven't really found that many stars like this. And it also seems like these stars don't really last very long because we've only discovered a small handful of these stars, and they all will probably go supernova as well in approximately a few million years or so. But in general, even though these stars are rare, they're still really interesting, mostly because they do seem to produce various effects here at the equator, including much stronger solar winds or stellar winds that would be, unfortunately, kind of really dangerous for any planet in the way here. So in other words, if this star had any planets here orbiting at the equator, and if they survived the initial supernova, they would now be irradiated with huge amounts of solar wind and very likely be stripped of any atmosphere and possibly even possess really unusual surface features that would only be possible when there's so much solar wind striking the surface. Although it is a lot more likely that a lot of these planets would probably not even survive the initial supernova, mostly because of the amount of energy generated by a relatively large massive star exploding so close. And there are very likely a lot more effects generated here by all of this really fast velocity. These stars probably have a lot of various stellar storms, they also have a lot more activity at the equator, but most importantly is that, well, at some point they will also go supernova, very likely. And once they go supernova, it's probable that they're actually going to create an extremely fast spinning remnant, most likely a neutron star. And not just any neutron star, but a neutron star spinning at close to the limit of fastest speed possible, very close to the speed of light probably. And because we've actually discovered really fast spinning neutron stars moving really fast across the galaxy, it becomes very likely that this is exactly how they were created as well, by these really fast moving stars that were created by a partner that exploded close to them. Although right now, this is not something we can definitely say with certainty. But anyway, it's definitely an interesting discovery of a new record holder for this fastest spinning star in the galaxy, with an average velocity of over 540 kilometers per second, creating this unusual shape that you see right here. And because a very similar star exists in our vicinity, in our neighborhood, it's actually kind of interesting for us to learn more about what happens to these stars eventually, and also if they do possess any unusual planets around them. Because this is something we would really like to investigate in a little bit more detail. But until we learn more, that's really it. Thank you for watching. Check out the paper in the description below, subscribe if you still haven't, share this with someone who loves learning about space and sciences, and consider supporting this channel on Patreon, because it does help me quite a lot. Or alternatively, you can also support this channel by buying the beautiful Wonderful Person t-shirt that I'm wearing right now as well. Anyway, on that note, I'll see you tomorrow. Space out, and as always, bye bye.